नहीं, मेरा Type J Miguel. Upon the chain.
2085.
Good.
Hi, Babu. Good morning.
Morning, sir. बिल्कुल सर
हाँ हाँ बोलो.
स्टार्ट करें क्या?
हाँ स्टार्ट कर दीजिए. मेरे को लगता है ऑलरेडी
Okay.
यू हैव कंपाइल्ड द क्वेश्चंस ना. So
Yeah. So,
I
good
mean this
morning.
is a question answer session. So yeah.
Let Dr. Babu first switch on the mic.
Yeah, he is started. Yeah.
Audible, right?
So, yeah. So, good morning to all. So, welcome to the second day of the session. And today we will start with the question answer session, which yesterday we could not take it up because of some technical issue.
This conference
So,
will now be recorded.
Dr. Babu will start answering the question which you have yesterday asked. So after that, we will have the talk of Dr. Surinder Rietveld. So maybe I'll hand over the mic to Dr. Babu, please.
Yeah. Hello, good morning to everyone, and also welcome back to second day. I will be answering the questions what has been sent to me yesterday. Some of them I have answered yesterday. I don't know whether I need to repeat it. Many people have asked about the B factor, temperature factor. Can it be isotropic? What is the significance? Basically, the B temperature factor actually directly proportional to the mean square displacement of an atom from its ideal position. So atoms are in a lattice, in a crystal, atoms are vibrating at any temperature, including 0 K, we call 0-point vibrations. As the temperature rises, atom starts vibrating more because you are supplying thermal energy to the system. Since when atoms are vibrating, when you imagine a crystal, we normally lattice means we fix points, but atoms are no longer fixed, but they are vibrating. So if it keep on taking snapshots, the atom positions are slightly shifted from each time. So that has some effect on the diffraction patterns and peaks. And this peaks is that diffraction pattern position of peaks does not change, but intensity does decrease with increasing angle. And the B parameter basically takes care of that by way of e to the power of 2w, where w is B sin theta by lambda. Since sin theta is B also moderated by sin theta by lambda, when theta is equal to 0, sin theta is 0. The whole exponential term goes to 0 and e to the power of 0 is 1. So that's why at low angles, the effect of B is not there. When you increase B, the effect of B becomes much more pronounced. So as a rule of thumb, let's say we can say for 1.5 angstroms, the B effect of B will be felt at maybe 2 theta angle of 80 K and much beyond. It is present at every temperature, but it is more prominent at higher temperature. What is high low? It is in relation with Debye temperature. For some sample, 300 K would be high enough temperature to see B effect of B at high angles. For some temperature whose Debye temperature is very high, 300 K could be low enough, B may be very small. So it all depends on the various parameters. And also, the atoms do not vibrate with the same amplitude in all directions, depending on its bonding, how many atoms with which it is coordinated, etc. So the B vibrations in some directions, it can be more, in some direction can be less. So therefore, B will be anisotrope in general. Theoretically, physics-wise, it is anisotrope. However, in a diffraction pattern, we remember that in a powder diffraction, it is a one-dimensional, three-dimensional information in a Fourier space projected onto a one dimension. A lot of information is lost. Therefore, the B, to start with, if you have to do any refinement or obtain B, you need to have good quality data. I'm saying, repeating, good quality data means you should have a good intensity, black peak with good intensity, let's say from 2 theta 80K and above. As high angle as better. 120 to 140 degrees. So quality of data you should have. I mean, with a good intensity. In neutron, we normally get decent intensity even at higher angles. X-rays, it is a problem. So that's why we generally say if you have a B, then you can refine B. B, not only overall B, there are, in a program, there are several ways to get the B. One is for entire compound, single B. That is called overall B. Okay, that parameter appears in the PCR file of full profs. First to scale factor, next to there is a shape factor, and next to it P parameter. B overall it's called. That is refined. To start with, one should refine that only. Overall B, and that too towards the end of the refinement. You almost reach within 90% or 95% of your correct refinement. If still it doesn't work, then you may go for an individual overall refinement. I mean, each atom, because if size of atom is different, its coordination is different in a particular unit cell. So the B's can be, each atom will have different, definitely physics-wise different B's. So that you can refine. B iso means isotropic. You don't again go for an anisotropic. That is a B isotropic for each individual atom. That is the next step. If somebody has a very good data, more so neutron data, going up to 140 to 160 degrees scattering angle, and high enough temperature where B can be important. Then after doing the individual B, one could attempt B anisotrope. So where now B will be have at least 6 parameter tensor. Okay, that can be done for each atom. So that is a very rare case you can do. Most of the time, normal XRD, I don't think B, overall B for entire compound should be refined only towards the end. Neutron, we can refine B, always should be refined, but always to the end. That is the situation about the B. B basically gives a measure of amount of amplitude of vibration, directly related to the square of amplitude of vibration. Okay. So other questions are, some of them I have answered. Just looking at the question, okay. Somebody asked what is a good data. Good data depends on signal to noise ratio. You have a peaks, intensity peak, and background is very small. That is the good data. Preferred orientation, how much for one phase? It depends. If a 1 or 2 preferred orientation can be allowed, not too much. What are the occupancy values for AB3O perovskite structure during refinement? Occupancy, as I said, for atom A is 1, atom B is 1. Oxygen may be at 2 positions, 1 and 2. That is the occupancy of fractional occupancy. It should be multiplied by site multiplicity, Wyckoff site multiplicity divided by general multiplicity of that particular space group. Suppose it is PNMA, general multiplicity 8. Wyckoff site, if it is 4C, 4. So you have to multiply that. For atom F, F means chemical occupancy, we will say it is 1 for A, B also 1, oxygen site 1, 1, oxygen site 2, 2. Software used to model neutron diffraction data into structural image. Full prof, and its suite has all the software. Phenol oxide, which of the 2 techniques is more better? I don't know what 2 techniques, probably XRD and she's saying neutron. Neutron is better. Neutron gives magnetic structure also. Why neutron scattering factor independent of Z? Neutron scattering factor independent of Z because it is It is a neutron nucleus interaction, which has nothing to do with the atomic number. Okay, it's a nuclear interaction. Can we confirm doping elements in any material by neutron diffraction? Yes, we are able to get cation distribution in one of the ferrite example I showed. So many elements are doped, we are able to confirm which atom is going to which site. How to figure out correlated variate parameter in a refinement R? How correlate? Actually, a correlation matrix is provided by the program, so from there you can tell. How to analyze data near Néel temperature? Okay, that depends. I assume by Néel temperature, you mean you're talking about magnetic structure. See, in neutron diffraction, like every instrument, every technique has some sensitivity. Similarly, in unpolarized neutron diffraction, you should have at least a magnetic movement of 0.3 Bohr-Manton and above to see the neutron diffraction intensity. So Néel temperature, the magnetic movements could be quite small. You may not see it. That is one problem. So if it is, you are very close to that. If movements are sizable enough, then you can see. Otherwise, no. Polarized neutron can be used, which can see up to 0.1 Bohr-Manton or so. Lorentz factor, effect of grain size and Lorentz factor. Grain size doesn't, Lorentz factor and grain size are two independent. Lorentz factor basically comes from a particular diffraction geometry. It is mostly due to the instrumental issues, and grain size affects the broadening in an indirect way because the diffraction peak gets broadened. So Lorentz factor and grain size are two independent things. Reason for spread of experimental spread in reason for spread of experimental spectra in FWH. I think why the diffraction pattern become broader as increase the 2 theta. That is the question seems to be. Basically, when you in a powder diffraction, as you increase 2 theta, that means you are decreasing d-spacing. With increasing theta, there are more and more d-spacing or Bragg peaks which are overlapping. The apparent broad peak that you may see, it may not be one peak, it is a multiple peak, 2 peaks, 3 peaks, many peaks. That is one contribution to the what appears to be broadened. Another, there is a geometrical reasons for of an instrument design, where you have the best resolution at certain angle. On either side of it, the full width at half maximum increases. That's because full width at half maximum as contributions coming from the spread in delta. Delta is not monochromatic. We say it is not strictly monochromatic. In case of neutron, there is a finite delta spread. Same thing with K alpha 2 is present in X-ray. And also there is various optical components starting from monochromator to the detector, the collimation angles before and after the sample. All this contributes to a Gaussian spread, and all this contributes to the full width at half max. So in general, it increases. Magnetic dipole, from where does the magnetic dipole come from lattice? How does it interact with neutron? Magnetic dipole, if you have a magnetic, let's say iron, the outermost electrons give rise to magnetic moment. That magnetic moment, if it is magnetic moment, unpaired electrons has a spin and has a moment. That will interact with the neutron magnetic. Question, can you determine the occupancy? This I already answered. Additional information, we get phase information, single crystal, which is lost. See, single crystal, additional information we get from phase information in case single crystal, which is lost in powders. See, in single crystals, in powder diffraction, there may be many times you may not be able to solve the structure. There are 2-3 different structural solutions may give same fitting, very good fitting. You will not be able to distinguish, or you may not be able to completely resolve certain situation. Then there is no option but to go to single crystal. Single crystal, you will be able to completely solve the structure. Okay, identify different structural models, which is correct. So single crystal will be able to do that. Neutron diffraction for thin films, we normally don't do neutron diffraction for thin films because neutron penetrates deep, and we need a very for a diffraction like similar to grazing incident X-ray diffraction. We don't have equivalent to neutron. What we do is what is called a neutron reflectivity, where you can get the several information about the film thickness, surface roughness, magnetic roughness, and if you have multi layers in the interfacial magnetism, all those things you can get from a neutron reflectivity. Does the refinement get affected with intensity to noise ratio, which may differ per sample? Yes. Quality of refinement also depends on the quality data. Quality data means intensity or signal to noise ratio, and sample to sample, if it's different, yeah, it will affect. What kind of significance we get when neutron diffraction patterns for non-collinear incommensurate magnetic? Okay, non-collinear incommensurate magnetic structure. When you say non-collinear, spins are canted or aligned, misaligned. Then if you resolve their component in X, Y, Z direction, it is possible in some direction you may have a certain amount of component pointing in the same direction. In some other component, it may pointing anti-parallel or totally unit. So if you see, you may have a signature which may mimic in a neutral diffraction, like a ferromagnetism and antiferromagnetic coexist. So new peaks will be coming, and some peaks are gaining in intensity as you cool from above ordering temperature to below the low temperature. So this kind of a thing is explained. Only after analysis you will know that is a non-collinear structure. Can we get diffraction of magnetic movements in collinear case? Yes. The control pulse spallation source we have not discussed here. I think most time how can you get an idea of neutron diffraction, particular sample, MT and MH? For MH, for example, MT is only showing paramagnetic behavior. If it is MT is only paramagnetic behavior, can be misleading. Like yesterday I showed BIF03, it is a G-type antiferromagnetic with very high temperature, but your magnetization data is only limited up to 200 K. You may miss the transitions. In that case, you may interpret as paramagnetic. Neutron diffraction, if it is magnetically ordered and the moments are size enough. See, neutron diffraction, when we say we can get signal, means at least the magnetic moment on a particular site should be at least 0.3 mu b and above. If it is less than that, magnetization can record even very, very small movements. But neutron diffraction, the sensitivity is not sufficient enough to see the magnetic order. If it is sufficient enough, you can see. I think some of this I answered. How much errors are FWH parameter occupancy? Errors are given in the refinement after in the output file. Is there any restriction on number of parameters? No restriction. But too many parameters can lead to wrong solution. Somebody, Chaitanya Verma asked, RP, RW weighted factor R expected is greater than. Is it a good fit? If R expected is greater than 10, yes, it is a good fit. You actually should decide based on RP. The R factor is only an indicator. Best way to tell the fit is good or not is to look at the diffraction pattern observed and calculate how close it is reducing, and also look at the difference pattern. Difference pattern will give the solution. That is the best test. Should we refine occupancy? Yes, it can be refined if you think, for example, oxygen occupancy in many manganetes, where you have a deficiency as occupancies are obtained from neutron diffraction. Not from X-ray is not sensitive for oxygen. But in principle, yes, oxygen occupancies of different. Suppose if you have some compound and you have doped with some element at certain site. You don't know which site, and that site has 2-3 possible crystallograph sites. You don't know where it is going. So you need to refine occupancy. How to decide occupancy values in refinement? I already told you. So we refine lattice parameter ion position separately, or we do simultaneously. Ion positions affect intensity, lattice parameter affect peak positions. So first thing to do, lattice parameter, you refine and fix it, then you go for ion position. Multiplicity, what is the difference between site multiplicity and general multiplicity? For example, if you take a PNMS space group 62 number, there are site occupancies, atom special positions or general positions. Most general position is 8 atoms it can sit. That is the general position of that particular space group. So general multiplicity is 8. For example, for site 4B, 4B means 4 site multiplicity is 4. That is a Wyckoff site. Wyckoff site name tells you the site multiplicity. And space group general position is given. If you look at the space group table, it will tell you, or even output file of the Pulprof also shows you. How to create an instrument resolution file. If you have to create an instrumental file, you need to run a standard sample, known standard sample, and generate the FWHM. Or put a single crystal and keep rotating, align it and keep rotating and track the rocking curve as function of thing. That is more difficult, but that is one best way. Otherwise, run a standard sample and create a instrumental file. If you are using defined background file, yes, you can skip the refining background. Somebody asked, if you have a background file, can we skip refining background after 0? Yes, you can skip. B cannot be negative. Yes, B cannot be negative. B is an amplitude square of, B is nothing but square of amplitude of lattice vibration. So how can there be a vibration amplitude can be negative? Physically not make sense. Similarly, occupancy cannot be negative. So whenever refining, sometimes parameters, it is a refining is fitting a mathematical. So some parameters become unphysically either large, become negative. So one should always keep a track that it cannot be, a site occupancy cannot be negative. It is meaningless. That means some atom is less than what 0. How is it possible? So physically some things are not sensible. So you one need to keep track of that. Similarly, occupancy cannot be negative. B cannot be negative. So those things you need to be kept in mind. One has to be careful in which parameter can be negative, positive, how much, in what range it should be, that one should keep in a. Atom position can be negative. Atom positions are given in the units of lattice parameters, 0 to 1. So atom position, let's say minus 0.1 is equivalent to 0.9. So there are still more questions. I think some of them I have answered. XRD peaks for copper FCC. What is UFCC? Copper, is it Cu0 or copper oxide? I don't know what is the question, not clear. Profile function for a given instrument is constant or varies with sample. Now, profile function basically depends predominantly on the instrument. It remains constant for once you determine a profile function for a given instrument, it remains constant. It doesn't depend on the sample. Sample only broadens, it does nothing to the shape of the profile function. What is the difference between void function and pseudo void function? When to use them appropriately? Void function is simply a Lorentzian and Gaussian mix in certain ratio. A ratio can be varied, and the Gaussian has its own full width at half maximum separate equation, and LAR engine has its own equation for full width atomic zone. Both are refined separately or weighted separately. When you, as a special case, if you assume that both should have same FWHM, constant single equation, that is reduces to pseudo void. Okay, that is the thing. Somebody is asking parameters, which parameter should refine first so that program will not corrupt, like instrument background occupancy. We have already given yesterday, somebody will again tell today also probably, that the sequence of refinement, first thing is to, first parameter always should be the scale factor. Next refine 0, then ABC, and together 0 and ABC. That is parameter. When I say ABC means lattice parameters. If angles are also involved, angles also. So these things fixes the, matches the your calculated pattern. There will be ticks where black tick should be, that will match with your observed pattern. Once that is done, then you can go for matching the intensities. Depending on if you have good FWHM, then you can go to start varying occupancies, atom positions, etc., etc. Or FWHM and other parameters. Values for B factors, value negative, I already answered. B ISO for XRD room temperature, yes. B parameter should be present at every temperature, except 0K where it is nearly you can put to 0. Otherwise, or 2K it is can be very close to 0. But other places, a finite value of B will be there. A rule of thumb, at room temperature we put B overall, not ISO, B overall for the entire compound as 1. Is proton diffraction possible? I don't know.
Muted.
In principle, it may be possible if you can produce protons. References, I think yesterday we had given, maybe today somebody else can show. Can we distinguish charge density wave and spin density wave? Charge density wave we cannot. Spin density wave we can see in neutron diffraction. In GD2, CU2, the fitting is different, is in different methods. So please make and understand what are the parameters we need to vary in pull flow. Okay, GD2, the last example that I showed, different, okay, moments are being refined. Moments and their angles are their Cartesian components are being varied. In addition, you need to model. It is not that one model, the magnetic model is simply, you simply vary all of them, you get the model. You need to model the magnetic structure by various procedures are there. Today or tomorrow somebody will discuss. It is not just simply modifying movements alone, you will get that structure. That's why I showed that example to show that it can be very difficult to get the magnetic model. You need a lot of work to do before you can get. I think I have mostly answered.
Yeah, it's already 10 o'clock, so I think.
Yeah, so we can close this. And if I only say that if there are, since today's talks also on Rietveld refinement and tomorrow also, some of these questions can be posed to the speakers and some of them can be answered by the either today's speaker or tomorrow's speaker as well. Okay, and some of the lectures of today and tomorrow also can clarify without specifically answering this question. And thank you very much.
Thank you, Dr. Babu.
Yeah.
This coming talk will also clarify most of the doubt of the participants. So now I would like to invite Dr. Rietveld to give his talk on Rietveld refinement method for crystallographic structures using X-ray and neutron diffraction data. Dr. Rietveld.
Thank you very much, Dr. Kaushik. And start all the way. Okay, I hope I'm audible.
Yeah, Sudhi, go ahead.
Yes. Yeah, you're on.
Okay. Thank you. So, good morning, all of you. And today being the second day, and we'll start with this tutorial. So we will try to build up on the foundation which Dr. Babu laid yesterday on the theoretical aspects and formalism of the retrieval refinement method. So what we'll try to do is that we'll build upon that. We'll see how the refinement can be done, and what are the information required before we start the refinement, and what are the information which we can derive from that. So the idea of doing retrieval refinement for us is that we understand the crystallographic properties or the structural properties so that we can correlate with our physical properties. So in order to establish this structural property correlations, we carry out this retrieval refinement mostly on the powder samples. So the plan of our presentation is that we will see how the powder diffraction works, what are the informations required, and what are the conditions for doing powder diffraction. We'll also go through the roadmap of data analysis, what are the steps involved, how to reach from sample to the structural data. And we're using some examples, we'll do using some of the examples, we'll see how to carry out retrieval analysis, what are the information required to generate the PCR file, and how the data collection can be done, and what are the steps involved in doing the retrieval analysis. And we'll try to see how the results look like and what information we can extract from that. Okay, so the purpose of powder diffraction is excuse me, is to understand the crystal structure. So the crystal structure, by definition, is of a material consists of the time and space average periodic conformation of atoms in an idealized crystal lattice. The powder diffraction also gives you a lot of information on microstructure, which are caused by imperfections, dislocations, and all kinds of disorder that are often responsible for interesting properties of material under investigation. So in the case that we are looking for structure property relations, becomes very important to look for. The studies of microscopic stress, like both residual from processing and in situ under load, are studied by powder diffraction. What it means is that when you're doing substitution, okay, you're replacing one ion, part of one ion by substituting by another one. So you're adding chemical pressure to that. Either it is a negative pressure or a positive pressure. And the effect of that pressure is reflected onto the crystal lattice, the structure, the bond lengths, bond angles, and that also has an effect on the physical properties. So if you can study these stresses because of this substitution or by applying external pressure, but by using powder diffraction, you can understand the structural implications of that. And powder diffraction remains to this date a crucial tool in characterization of materials with increasing importance, and reach of application as instrumentation methods, data analysis, and modeling have become more powerful and quantitative. There is always a debate between single crystal and powder diffraction. Of course, single crystal diffraction is important if you want to look for a new crystal structure. If it's an unknown compound whose structure is not known, then single crystal diffraction becomes very important. But there are cases where you can't get single crystal of every element of suitable size or quality, which are useful for single crystal diffraction. So in those cases where no single crystal data is available, or it's not necessary to prepare single crystals for every compound, powder diffraction is the best and nearest alternative which we have. And also the single crystals also does not provide information about the bulk of the material. This is not a routinely used technique for determination of microstructural properties. So neither it is often used to characterize disorder in the materials. Although the powder method was developed as early as 1916, about 100 years ago by Debye and Scherer, in the first 50 years of its existence, it was used exclusively for qualitative and semi-qualitative phase analysis because the limitations of the basic programs or the methods. And it was also used for looking at the macroscopic stresses also. The principal problem of powder diffraction is that there is a systematic big overlaps because of the projection of a three-dimensional reciprocal space onto one-dimensional 2θ axis, leading to strongly reduced information content compared to a single crystal data set. So this is a limitation which we have to accept when we are working with powder diffraction. However, Despite the loss of this angular information, there is often sufficient information which resides in one-dimensional data set, which will be helpful in reconstructing the 3D structure. So this is the basic purpose of doing Rietveld analysis, that you start from a sample, you carry out a diffraction measurement to record your diffraction data, and you analyze this diffraction data so that you can conclude with the structural data, structural information. Now, if you look into the powder diffraction, there's a lot of information buried in that. And what are that? You have basically a background and reflections. But if you go deep into that, the background can be from the sample. If it is from the sample, it can be because of component scattering or diffuse scattering. And if you can model that, and if you can include in that refinement, you can understand about the local structures, amorphous fractions, and lattice dynamics. The background can also be from the sample holder, the way you are measuring your sample, the diffraction patterns. It can be from air scattering also. And so therefore, if you can quantify sample and background from sample and scattering, you can get some more information about that. Another part of a powder diffraction pattern is the reflections, which are basically the Bragg peaks. It tells you about the position of from the position of the Bragg peaks, from the intensity, and from the profile shape function. You can derive information about the crystal lattice, crystalline magnetic structure. And you can, if you do the qualitative analysis of this, you can understand about the micro strains. You can understand about the atomic positions, occupancies, which will tell you about the cation distribution. It will also tell you about the thermal parameters or the temperature parameters. It can, if you are looking at magnetic structure, it can tell you about magnetic moment, texturing, and so on. The profile shape function has two components. One is the instrumental function. Largely, it is of the U, V, W, X, and Y. Most of them has a contribution from instrument, but some of them, like U and X, Y, have a contribution from the sample also. So if you can model that, you can look into the micro strains, domain size, and so on. So in a real powder diffraction, there's a lot of information for it which can be extracted and is useful for the analysis. So if you look into the roadmap for structural refinement, we have to start from a sample, and we have to go up to a stage where you find the information about the structure. The road looks straightforward, but actually it is not. You have to go through several steps. Like you have to choose a radiation source, you have to collect your diffraction data, good quality diffraction data. You have to process it. It means you have to index the data, you have to determine the space group, which kind of space group it is. Then you can justify this too by using this profile fitting, either Liebel method or Hollis method, which are part of the direct, what is called the direct methods. Then once you have confirmed that, you can actually go supply the chemical information, the unit cell, contents of the unit cell, the atomic positions, occupancies, and all. And then you can carry out Rietveld method to reach to the final destination, that is the final structure. Okay. So the first step of this roadmap is to, of course, prepare sample, but then you have choice of different radiation sources to collect the diffraction data. You can use lab source X-ray, or you can use synchrotron XRD. You can use neutrons, continuous wave neutrons like reactor-based ones, or time of flight measurements, which can be done at the spallation neutron sources also. So once you have collected your diffraction data, okay, the choice of the radiation depends upon the purpose which you are doing or which is accessible to you. So yesterday we have seen in Dr. Babu's lecture that there's a variation or there's a difference in the way X-rays scatter or neutrons scatter from the samples. The X-rays have strong Z dependence because the X-rays are scattered by the electrons, electron cloud in your sample. So they have, the more the electrons, the more scattering it will be. So it has almost Z dependence as a function of the Z dependence for the scattering amplitude. Whereas in the case of neutrons, since the neutrons are chargeless, they can penetrate deep into your sample and they can interact with the nuclear energy levels and they get scattered because of that interaction. So you don't see a variation, linear variation. It is always irregular variation as far as the neutrons scattering is concerned. But if you look at the scattering amplitude as a function of the scattering angle, the X-ray form factor falls off as a function of the 2 theta d. Whereas in case of neutrons, it has a steady, or you can say flat neutron scattering across all the angles. What it means is that in case of X-rays, you see that the intensity going down as you go to the higher 2 theta. Whereas in case of neutrons, you get a similar scattering at all angles. Now, then you have to choose the instrument or the geometry which this instrument employs. Most of these X-ray instruments, either it is lab source X-ray or at the synchrotron, it is basically the Bragg-Brentano geometry, which is basically the reflectance geometry. Means you are actually working in the reflection window. So you have X-rays falling on a sample, gets diffracted, and it's collected by the detectors. And this is a typical XRD pattern which you get for your sample. This is an example for calcium gold manganese oxide, which is measured using CuK alpha at room temperature. And in case of neutrons, if you measure the same sample, the neutrons passes through the sample and gets scattered and is collected by the detectors. This is called the device error geometry, or this is also called the transmission geometry, because the X-rays, or sorry, neutrons passes through the samples and gets scattered. For the same compound, you can see that this is a neutron at roughly same wavelength at room temperature, and this is a diffraction pattern for that. I will tell you why the difference is there. Once you have collected the diffraction data, next step is to process the data. First is to index the data. Okay. What do we mean by indexing is that when we do the diffraction experiments, we see different Bragg peaks. This Bragg peak is a diffraction in the diffraction pattern is observed because of the diffraction from a particular plane. Therefore, the indexing is a process by which these reflection indices, like HKL values, are assigned to the peaks in the diffraction data. The purpose for doing that is that as soon as you have sufficient number of reflections or HKL values for certain peaks, you can calculate the unit cell parameters. And when you compare this with the single crystal data, because in single crystals you measure reflections in all three angular parameters like omega, psi, and phi. So you collect HKL reflections in all possible orientations. So it gives you a bunch of data, which is easier to process when it comes to powder diffraction. So powder diffraction indexing is a little bit tricky, but it is very important step to do that. So these are the diffraction Miller indices which we see, and this, depending on the reflection, what you observe in diffraction pattern, you assign that. So how do you do that? Is to compare the diffraction pattern of your sample with the known sample, which is either chemically or structurally identical to your diffraction data. The best way to do that is to look into the database, compare it with like PCPDF or JCPDF database. So this is an example for sodium chloride. This is the diffraction pattern for the sodium chloride. So what we do is that once you measure the diffraction pattern by using Bragg's law, you can convert 2 theta into these spacings. So you have these spacings and you have intensities for these spacings. Depending on comparing with this PCPDF data, you can actually assign these HKLs to the corresponding Bragg peaks. So you have HKL values, you have these spacings, and using that you can calculate the cell parameters. So from the crystallography, we know that we have 7 crystal systems, and they have some certain conditions as far as their unit cell parameters are concerned, right? For triclinic, like all 3 unit cell dimensions, ABC, are not equal, and all 3 angles between this axis are not equal also. Like that you have for monoclinic, and for cubic, like that you have all for cubic. So in case of cubic, ABC is same, and alpha, beta, gamma is 90 degrees, and they are all same, right? So this is how this is expressed in reciprocal space. Now, on the basis of the HKL and D values, you can calculate the parameters. Like in case of cubic, you have only one sun parameters like A to be calculated. So if you index one Bragg peak, you get a value for that, and you know the D spacing for that, so you can calculate the cell parameters. Similarly, these are the equations for the different lattice systems, crystal systems. Now there are several programs available which for carrying out this indexing method, something called ITO, which is good for unit cells of compounds with low symmetries like monoclinic, triclinic, hexagonal, and all that. Then something called TRERA, which is basically short form for trial and error. This is can be done for cubic, hexagonal, tetragonal, basically all crystal systems. Then there's something called Rietveld, which is also useful for high symmetry crystal systems. The one of the most important requirements for doing indexing is that your sample quality should be, the data of your sample should be very, very good. If it has a lot of noise or background is too high, then you will not be able to pinpoint on the actual solution from that. And then there are several other programs which you can use for doing it manually. Means you can calculate HKLD and it will use the least square method to calculate the cell parameters. So there is one program which I generally use, which is called PowderX, which is which employs this Visual Basic and Fortran version of Trailer 90 program. So the method is simple. Once you plot your XRD data, you can actually identify the peaks. So this is what the information you get. You get 2 theta, you get D, you get the intensities and the half widths for that. And the program, once using this the peaks which are already indexed, you can use this indexing program called Trailer. You can use this current peaks, start the program, and it will go through this several cycles, try to test all cubic crystal systems. And if it finds a solution, it will tell you what solution it has found. And the result it shows you that it has chosen a symmetry class of hexagonal with the p-type lattice and some cell parameters. This is how it shows in the output file. Once you have this in starting cell parameters and this crystal system, you can actually do the peak match. That means you can assign the HKL values to these peaks, and then you can ask the program to do the cell refinement. So this is what it gives you as an output, which means you have starting HKL values, ABC values, and you end up refining these values. What it means is that you have indexed your HKL values, you have HKL and D values, and on the basis of that, you have defined the cell parameters. Once you have this HKL and D values and unit cell parameters, the next step is to look for this appropriate space group. Our indexing program has shown that for this system, which we are trying to, the example which you are using, it can be hexagonal and it can be trigonal because they are closely related in crystallography. So these are the possible space groups, one of which will be the appropriate one for refining the structure of that sample. So one way of most of the indexing programs like Trailer and Rietveld can give you an integrated intensity file, and using that you can actually check what are the space group it suggests using the check space group program in the foolproof toolbar. Or you can actually go through the literature and try to see which is the correct space group which will define the which will actually satisfy the HKL conditions and systematic analysis in your space group, and accordingly you can pick a space group from that list. So once you have the space group, once you have the starting cell parameters, you also have the diffraction data with you. The next step would be to do a label fit to ascertain whether the space group which you have used actually is useful for that or not. The advantage of doing this is that it will tell you whether your sample is single phase or not. Okay, before you actually put in the structural model and do the required refinement, you can actually ascertain whether your sample is single phase or not. So that is the advantage of doing the indexing program. The Liebman method actually works on the extraction of intensities from the powder diffraction pattern. So it doesn't do any scaling, but it will take the intensities from the diffraction pattern which you already have in your data. And you can define several parameters like unit cell parameters. You can correct for instrumental zero errors. You can actually define the half widths. You can define other peak shape functions. So before actually you start your Rietveld analysis, you can actually define all these parameters and keep it ready. And the next step would be just to add this information. So this is a typical PCR file which can be used for the legal fit. Okay. So if you look at the PCR file, there are several numbers which you are given there. And if you go to that, say for example, job type here, in this case means the X-ray case, which means I'm using X-ray diffraction data to define the X-ray data. Okay. So there are other options. You can use neutron refinement. You can do X-ray pattern calculation. You can do neutron pattern calculation. Similarly, you can do refinement using time of flight data, or you can calculate the pattern using the time of flight data. So like that, there's several information which are available on the in the description of the PCR file. So to get into the this foolproof manual, there are several manuals in PDF or ASCII format. There is one HTML format also, which you can open in your browser and actually go to this description of a code file, PCR file, and you can get information about each line of the PCR file. Okay. Now, if you look into the PCR file, this is the portion which is actually responsible for doing the label fit. So information which you have provided here is that you are asking the program to do the label fit, that is intensity extraction method. You are giving the space group, you are giving the starting cell parameters, and rest of them are the instrument parameters like half widths. Okay, and you are also giving the wavelength, which tells you the radiation which you are using. It can be X-rays, it can be neutrons, and you are providing some background points for the program to interpolate. So when you start with a PCR file, and you have to have a data file. So using these two, when you call the program, use the program, you call the PCR file, and this is the fit which looks. So what it means is that if you start with a cell parameter and a space group, which is close to, which gives a correct solution, you get a good fit in the lipid profile. So far we have only done the refinement of the cell parameters, and using the space group, we are trying to match the observed data with the calculated data. So when you look into the output, it generates so many files. Like in addition to the PCR and that file, it has created one HKL file, which is the integrated intensity file. If you don't get it from the Trello default program, you can use this file and use the check cell program, check space group program, and you can identify what space group it suggests. Okay. Then there's some called summary file, which is the summary of all the refinement results which are put into that file. Then this is the PRF file which is generated, which can be used for looking at the profile in WinPlot app. There is some output file. So all the refinement values, except for including the last cycle, are put into that output file. And we have used PCR2, which Dr. Babu explained yesterday, so that I don't want to overwrite my PCR file, but to generate a .view file. Okay. So all the information, refined information, is put into this new PCR file. So if this is the PCR file before I started the refinement, this is how the refinement looks like. The PCR file looks like after the refinement is done. So what it does, that it has generated this HKL file and it has flagged it as IRF2. So whenever I want to run the label fit again, if I want to use the same file again, it will look for this HKL file. Okay. If you don't have that HKL file, you can keep it 0 and start all over again. Okay. These are my refined cell parameters at the end of the full label cycle. Okay. And then the next part of once you have got the label fit, which means that you have got a space group which is correct. We have got some cell parameters to start with. We have instrumental functions which are already normalized or optimized. The next step is to add the structural information. So the example which you are using is this calcium cobalt magnesium oxide. So by chemical valence, I have calcium 2+, cobalt is 2+, and manganese is 4+. I have one anion, which is oxygen, and the valence is 2-. So if you, for ionic bonds, you know that it has to be chemically stable, so that this is charge balanced. And what I need next is from the space group is the site symmetries or the site positions or Wyckoff positions. Okay. So one of the best ways to look into the Wyckoff positions is to go to this Bilbao crystallographic server, which is available here, and then you can give this space group or space group number and get this information. If you don't want to do that, you can look into this tools which is available in the WinPlot app. Go to the space group info. Sorry, it should be space group info, and then you can actually write this space group, or you can even tell the space group number, like 167 in this case, and you can get this information. So what it tells you is that the general multiplicity for this space group is 36, which means there are 36 symmetry operators available in this space group. There are certain special Wyckoff positions which are available. It doesn't show you the general position, that is 36F, which we have seen. So you can choose to place your atoms in one of these Wyckoff positions, but you have to be careful about the stocking material. So what are these special which I have marked is that for R3C, for the compound which I'm working on, these are the 4 positions on which I can place my atoms, or where the atoms are placed. Okay, so I have site multiplicity of 18 for this bicopletter, which means the translation. These are the positions which is actually X014. If you see this here, this is this position 18E. Similarly, this is cobalt is at 6A position, which is 0014, which is you can see is the 6A position. Like that, you have manganese at 6B. This is 000, which is basically the you can consider as the origin of the unit cell. And oxygen is at 36. It is XYZ position, which is basically the general position. Okay. What the idea of having site multiplicity, the purpose of having site multiplicity is to calculate the occupancies. The occupancy, that means 100% occupancy of my site is of this particular site is the site multiplicity divided by the general multiplicity. So for this case, for R3 bar C, we have seen that the general multiplicity is 36, and site multiplicity for calcium is 18, so its occupancy should be 0.5. So like that, you can assign the occupancies for each of the atom based on the site multiplicities and general multiplicities. So the information which I'm looking for that in my composition, if I want to see the ratio, this is 3116. Okay, this means 3 moles of calcium, cobalt, one is for cobalt, manganese, and 6 of oxygen. So if you look at the site multiplicities, they are in the same 3116 ratio. If you look at the occupancies, which is actually related to this, is also in the same ratio. Okay, so which means that my stock occupancy is correct when I start with my refinement. So once you have all the information which is required for Rietveld method, the next is to apply the method and reach the structure. Of course, this is not a straightforward anyway. We have to go through several crystals and splits and runs. So we'll see what are the advantages and disadvantages before we actually go into the refinement mode. The advantages of Rietveld refinement method is that it uses the intensities or the diffraction pattern as it is. We don't do anything with the diffraction data. We use it as it is for the refinement purpose. Okay. The best advantage of using Rietveld method is that if you use the entire spectrum, don't restrict your profile. Use as wide range as possible. Okay. Since in case of X-rays we are limited by the intensity, so we restrict to like 10 to 80 degrees or 20 to 80 degrees. But in case of neutrons, you can have, depending on the instrument, you can go up to 120, 140 degrees as far as your instrument allows. The advantage of Rietveld analysis is that it can do qualitative phase analysis. You can determine lattice parameters, atomic positions. You can refine atomic positions, get the correct positions. You can get the correct occupancies, which is useful for cation distribution. You can get the thermal parameters. You can also find out the grain size and microstructures. And the Rietveld method, as you will see tomorrow, is the best way of determining the magnetic structure, and which helps in correlating the structure and the magnetism and physical properties. But the disadvantages of Rietveld method is that it requires a starting model. So what we are actually doing is that we take a starting model and we try to refine that model so that it fits to our observed data. So some prior knowledge of crystal structure is needed, so then you can actually determine your starting model. And as you would have, some of you might have already experienced, Rietveld programs are not easy to use. It requires some experience to handle the programs and analyze the border diffraction patterns. I would like to mention here that don't treat it as a holy grail. Whatever it gives is not always correct. Treat it as a newspaper. There's some useful information. There can be some garbage depending on how you refine that. But the information which you get from refinement is actually correct. You have to validate it. It is your decision how to use that information and how accurate it is. So once you have that information, you can actually go for the structure property understanding and you can process it further. The method which it employs is that it takes a crystallographic model and computes a diffraction pattern and it compares it with the experimental diffraction data. The program, what it does is that it's trying to minimize the difference between the experimented and the calculated difference pattern by using this quantity, which is like the weighted sum squares, which is actually trying to reduce the difference between the squares of this observed and the calculated intensities. And we have seen this equation, which is basically the intensity calculation equation, which comprises of several factors. We'll touch upon that in a minute. So the necessary condition in refinement is that it carries out refinement in cycles. It goes to different cycles. We determine the number of cycles it should go through. The quantity it is trying to do is that it is trying to reach the minima for each quantity which is being defined. And when it reaches the minima, it converges. The conditions for conversion depends upon the values which are given, which are used, like the number of intensities, the cycles it goes through. It depends upon the parameters which are being defined. Okay, and the minima, how far it is from this ideal position. The shift of these parameters are obtained by solving these normal equations, and which are added to the next set. Okay, so from one cycle, the defined values are added to the next values, and it goes to the cycle till it reaches convergence criteria. Okay, some of the information which it uses for refinement, I mean, for the cyclic iteration process, is actually based on the input which we provide, like number of atoms in the unit cell, number of parameters being varied, and number of constraints we are giving, a number of the counts of the data. Okay, the least squares procedure provides, when it converges, the value of the parameters constituting the local minimum closest to the starting point. So if it actually will, depending on the tolerance which you are given, it will try to optimize or get a value which is closest to the ideal value by converging to that value. So the best quantity or the most important criteria is to have a good starting values. So your starting model should be very good, and means you have to actually check whether the space group is correct, whether the cell parameters are identical to your compound which you are trying to refine. So that's why the initial model has to be very good. If you start with a bad model, you will never reach the convergence, and your refinement will always diverge. What I try to say is that if your sample is hexagonal, if you are trying to use a qubit model, you will never reach the solution. So you start with the correct model, and you can optimize this model to fit to your observed data. Now we have seen this structure factor equation yesterday. In case of X-rays and neutrons, it looks, most of the time it looks the same. It takes the same information about the H-scale values, takes about the angular range, the thermal parameters, and so on. The difference you will see is in this structure factor, and this is the thermal parameters. So in case of X-rays, you have the structure factor, X-ray structure factors. In case of neutrons, you are working with these thermal neutron scattering lengths. But the purpose of doing refinement is that you calculate intensities, which is square to the structure factor. So we are always trying to obtain the intensities from refinement of the calculated pattern, which should be square of the structure factor. So this is the example. We come back again. This is XRD data. This is the neutron data, and the difference here is mainly because in case of X-rays, we are using these scattering coefficients. In case of neutrons, we are using scattering lengths. The advantage, of course, biased towards neutron again, is that in case of X-rays, you see that cobalt and manganese, they're placed next to each other on the periodic table. They're one electron apart. Then the scattering is almost identical. So you are not able to distinguish between cobalt and manganese when you are refining the XRD data. But in case of neutrons, you have a very good contrast between cobalt and manganese, and you will be able to actually distinguish between cobalt and manganese contribution. So this is an advantage of using both X-rays and neutrons. But the same structural model can be applied to fit both the diffraction data. And this is one of the examples I'm going to show you today, how to do this, how this is. Yeah. Okay, now coming to the profile, this intensity equation again. So this equation is made up of several factors, or you can say parameters. This depends upon the phase, depends upon instrument geometry, depends upon the sample. And each of these quantities in this equation can be written in terms of parameters. And this is what we'll be doing when we do the refinement. And it can be optimized. So first is the scale factor, which is given by this equation. And the scale is the first factor and always on, which means we'll always try to refine the scale factor. The purpose of scale is that we are trying to put your diffraction pattern on the calculated pattern on the same scale so that they should match. Okay, that is important. Then there is something called Lorentz polarization factor, which depends upon the instrument geometry, You can be using X-rays, you can be using neutron instruments. So it depends upon that quantity. Next is the structure factor, which we have already seen. So the structure factor basically has information about the sample position, HKL values, and the position XYZ values of each atom. So this is summed over for all the atoms in the unit cell, which we have specified. Then is this profile shape function. So it again is the instrumental fraction, depends upon the instruments. Then you have some symmetry conditions, because the space group which is specified will determine the number of Bragg peaks which are allowed in that space group. And number of peaks, for high symmetry you get less number of peaks. For low symmetry systems like triclinic and monoclinic, you get a large number of peaks. So that's determined by your symmetry. Next is a preferred orientation. For an ideal powder diffraction, you expect there should not be any preferred orientation. For some values, you can actually refine and see if there is some orientation because of the way sample is prepared for experiments. But there are some groups, some work which is done texturing also. The sample is in such a way that you have reflections along certain lines. So that can also be accounted by using parameters. In most of the cases, either it is a reflectance mode or transmission mode, there are chances some of the radiations. And once the beam passes through a sample, there are chances that your sample can absorb some of the radiation. So there is some correction for that. This is for the absorption quantity, which can be specified. And of course, there's a background. We have to tell the program from where to calculate the intensities. So it has to specify the background. There are polynomial functions available. You can also specify the number of background points. Answer that is how it should work. Then there are different R parameters. We have seen this. And most important is that the refined parameters. These are indicators as we what it is that it is the intensity of the observed data. This is the calculated intensity, and this is a ratio of that with respect to the intensity. Then there's something called RWP, which is the very important criteria. You have some knowledge on that.
Permission മേടിച്ചിട്ടുണ്ട് നാളെ വരാവോ എന്നിങ്ങനെ ചോദിക്കേണ്ടി വരും.
Okay.
I'm muted.
Please.
Sudhindra, your mic is off.
Yeah.
Sudhindra?
Yeah, now it's okay.
Yeah.
Thank you. I'm sorry for that. I didn't know. Yeah, the acceptable values for RWP is for some medium and complex phases should be around 10. Less than 10 is always better. For low symmetry systems where you have more overlaps of Bragg positions on complex structures, it can be around 15 or less than that. For high symmetry, anything around 8 or less than 8 is an acceptable value. For samples with high background, you should always look for RWP with this data in which you have subtracted background. And R expected is the minimum RWP value it can reach, because as if you have seen, the goodness of fit is the ratio of these two. So it cannot be less than RWP, then it will be less than 1. So the minimum value it can go is of goodness of fit is R is 1. So which means that R expected should be more than RWP. Okay. The weighted sum of squares, that is SY, is only used for the minimization routines, and its absolute value depends upon the intensities and number of points. Okay, so if you have good quality data and number of points are reasonable, then it can converge faster and give you reasonable values. and the goodness of fit value, which is acceptable, is like your chi-square should be around 2, but it is not always the better criteria. Okay, so it can tell you about the inaccuracies in your model or in your data, but the point is that it should be as reasonable as possible. The most important criteria is to visually see how good or bad your fit is, and then you should look at the RWP values, which will give you a fair idea of how your refinement is progressing. Now, when you start the experiment, you have to choose the correct instrument. You have to choose which, depending on the sample, you have to choose your experiment. If you have a gadolinium-based sample and you want to neutron, it may not be possible because gadolinium has very high absorption of neutrons. So accordingly, you have to choose, depending on your sample and the purpose, you should choose your experiment or instrument. You can do select the experimental conditions, means you can do X-ray as a function of temperature, neutron, depending on your purpose. You can also do as a function of field, pressure, and any other criteria. You can prepare your sample according to the choice of your instrument and the way it has to be mounted. For powder diffraction, your sample has to be as finely grinded as possible so that you can avoid preferred orientation. And you have to prepare it in quality which is suitable for the method which you are using. You have to always verify the quality of the data which you get. Most of the neutron, you work with some other group or some other instrument scientists. You have to make sure that you always get good quality data. That is true for X-ray cases also. If you're not doing yourself and you depend on others, you have to make sure that the X-ray quality which you're getting is reasonably good. Okay, then you have to choose a correct model, and then there are several steps involved, like determining the cell parameters, background parameters. You have to refine the cell, you have to refine background, peak positions, shape, thermal parameters, so on, and you get results for the structural refinement. The successful return analysis depends upon the quality of your data and the instrument characteristics, choice of the instrument options. You should also look into the range, the 2-theta range as wide as possible. Step size will tell you about the resolution of the instrument. X-rays have better resolution than neutrons, so X-rays will give you better cell parameters than neutrons. But neutrons can give you more information about the position, occupancies, and all that. So these are always complementaries. The amount of time you get data. Okay, so the better the statistics, the better the data quality will be. And you have to prepare sample conditions according to the experiment which you are trying to do. Now the choice of programs, of course, there are several programs which are available, like GSAS, Foolproof, Mod, Rita, and DWS. These are all freewares which are available over the internet. And there are some commercial softwares also for like PGM and Topaz, which are available. We have been using Foolproof because we find it very versatile and very useful for both structural as well as magnetic structure refinement. And one of the reasons which I told you to download Foolproof is that it is free and it is always available. It is continuously under development after so many years, and you always get a latest version of that. And now it is available in 2 different operating systems, security bits like 64-bit and 32 bits, depending on the operating system. So this is most versatile. The best part of Foolproof is that it comes with many inbuilt modules or programs like Foolproof Studio, which is useful for visualizing the crystal and magnetic structures. It is very useful when you are working with magnetic structures. Then you have WinPlotter and WinPlotter 2006, which are basically GUI-based programs for plotting and data, and actually for carrying out Rietveld refinement. Then you have several programs like Faults, Foolproof. This is like non-GUI-based interface for carrying out Rietveld refinement. Then you have EDPCR, which is used for editing the PCR files, and you can use it for writing a new PCR file also. I will show you an example how to do that. Then there is a K-search program which is useful for identifying propagation vectors when you are working with magnetic neutron diffraction data. Then there are some indexing programs, as I said, which are available here. It can also be run through WinPlotter, and this is called Dickfall and Trevor. You can use WinPlotter 2006 or 2000 or WinPlotter to run the Dickfall from outside also. Then there is something called for checking space group, as I told you in my slides, few slides ago, that it can be used for checking the space group from the indexed data. And there's something called data read for reducing the single crystal data and using it for the diffraction purposes. There are other options also, which are like G Fourier, then bond star program for calculating bond star, bond lengths and bond angles, bond valence sums. Then Basireps is useful for, you'll see tomorrow that it is useful for calculating the basis vectors for reducible and reducible representations. And there is something called Vesta also, which is available here. This is a link actually. Vesta is not part of the foolproof suite, but you can download Vesta and you can link it to this, and you can use Vesta as part of it. You can use it for visualizing the crystal and magnetic structures as well. So to get started, you need a PCR file which should contain about the crystallographic and magnetic information. If you are working with crystallographic data or magnetic data, it should have contain information about the instrumental resolution, background, and so on. And your data files consist about the experimental data files. There are many data formats which the foolproof can read. I will show you one or two examples of that. And when you start the refinement, it will use the PCR, it will use the data file, and it will do the refinement, and it will generate most of these files. Okay, so if you are looking for the if you are enabled the bond star or the bond length calculation or bond valence sum, it will give you that distance file, which is bond length, and bond angles and bond valence sum file. FST file is useful for looking at the crystal structures. Depending on the phase number, it will create one FST file for each phase. Summary is file, or the dot sum file is the summary of the last cycle. All the refined results of the last cycle are stored in this. All the files, if you allow the program to calculate, to create a new file, it is basically a PCR file with the refined values. And all the information from all the cycles are stored in this output file. There are a number other files also generated depending upon the flags which we use. Okay, to start with, you start using this EDPCR. You can calculate it, and you can actually start writing a new PCR file depending upon the crystallographic information and the instrumental functions which is available with you. Or you can use this toolbar to calculate. And if you have a CIF file, that is crystallographic information file, you can actually calculate to use that to create a PCR file. The CIF file is available from different databases like ICSD, ICDD, and Pearson Crystal Data, and there are other open source available sources like Crystallographic Open Database, MinCrystal, and Cambridge Crystal Database. Some of them are subscription based, so it has to be subscribed by your library or your institute. But there are some with some limited numbers of data structures available on these databases. Okay, so just to get started, there are several examples which are available in foolproof installation. If you have installed foolproof, you can go to this examples folder and you find number of PCR files, number of data files for each of these PCR files. You can use them for practice. If you don't have your own data, you can use them for practice. And you can use these PCR files, you can modify them according to your starting model. You can create your own PCR files by editing them. That's why I asked you to use an editor. Either EDPCR, you can use a text editor to replace and modify these PCR files. You can use it for your purposes. Or you can also use CIF files to generate the PCR file and start your refinement. So at this stage, I would like to go back to my slides. I will show you, demonstrate how to create a PCR file, how to use it using X-ray and neutron diffraction data. I will show you one example in which we can add a secondary phase. You can identify impurity phase, add a secondary phase, and do the refinement. And I will have one example to show you how the size and microstrains can calculate. Okay, so I will. So I will minimize this, and I hope my screen is visible so I can show you the refinement. The first step I thought of showing you is that how to do a level fit. So this is the PCR file which I was showing you in my slides. So this is based on the information which I had done by indexing. So I have this provided the space code here. I have asked the program to calculate, do the level fit. So I don't have any other structural information. So the number of atoms is 0 here. And I have provided the instrumental parameters that is UVW, X and Y, depending on the instrument which I'm using, and the cell parameters ABC and the angles of between that. And I have also provided here the number of background points. So how do I get the background points like this? So I can import different formats of data points. Okay, you can the foolproof the vim plotter can read several formats. The format I'm trying to show you today is this is my data file. This is actually in 2 theta format, 2 theta and intensity format. So this is my 2 theta and this is the intensity for that position. So this is one format. So I have to tell the program. So somewhere here I have to tell the program what type of format I'm using. Okay, so in this case, as a foolproof reads, it can, when you call this XY data, this is my free format data. So if I have data in XY, the instrument resolution, the code for that is 10. So I have to specify the 10 programs. So if you look at the PCR file carefully, there are 2 parts of that. One is this part, where you actually tell the program what to do, what type of files to generate, what type of input you are giving, and what type of variation you are using. You are not defining any of these parameters. These are all fixed quantities which you are inputting. But there is another part of the PCR file where you are defining parameters. Like you're refining these cell parameters, you can refine the half width, you can refine the scale, you can refine the thermal parameters, and so on. But for the case of fit, we are going to just refine the cell parameters. That is the only parameter I want to refine. So ideally, the instrumental 0 should be 0, because what it means is that when you start the experiment, the instrumental 0 should be actually at the 0. It means the starting point of your diffraction pattern, right? So I start assuming that it is 0, and I can refine it later depending upon how the peaks shifts. So when I call my file, so I can call my file, and this is how the X-ray data of this sample looks like. Okay, so I can choose the points. I can go automatic background depending on the threshold levels, noisy data or not. I can actually generate this automatic background files. Similarly, I can call this again. Okay. And I can actually select the background points. Okay, I can okay, what I will do is I will plot it. Okay, I can actually zoom it, and I can go to point selection. I can actually select the background points. Okay, and actually, and once I do that, I can save this background points. When I do that, this is how it saves the background points in a certain file. Okay. So once I have collected the background point, I know some of the basic information which I need for PCR file. Okay, I have added the background points. I have added the information about the space group and cell parameters. So I'm set to do the refinement. So I can call the program, call the PCR file. And what I generally do is that I generally keep the file names same. The PCR and DAT file have the same file names. So if I have the PCR file, it will just run because it knows which data file to ask. Otherwise, it will specify what the point is. So at this stage, we are defining only the cell parameters, not even the background. This is how my label fit looks like. So what it tells me is that it is taking care, indexing all the track peaks here, which means I don't have any impurity at this stage in this sample, and all peaks are accounted for by this space group. So I can call the new file. So you can see that it has generated so many files. I can call the new file, and you can see that it has changed these cell parameters, okay? And it has actually calculated the HKL file, which means the integrated intensities. If you look into that, and you can call it in this text editor. And this is the format. This is the HKL, and these are the reflections position wise as well as truth intensity wise. Okay. So this format actually I can show you if you want to test it. You can use this check space group. You can call that file. So I call it some name. Okay, I can call this file, and it takes all this information from this file, and I can run that. Based on the refinement, it will give some suggestions about the space groups. Now it is for me to decide whether these space groups are correct or not. For my experience, this is not giving me a correct solution, but this is the step you can do when you don't know, you have no idea about what type of space group or structural parameters your sample will have. So this can be the starting point. But say if it is not correct, it will actually go in many cycles, and you have to actually determine the correct space group. Assuming that you know your space group is correct, so this is how you can define your cell parameters. If you look into the sum file, it can give me the actual cell parameters which has defined along with the error bars. So at this stage, I wanted to confirm that my space group is correct, my cell parameters are defined. So this is how you can start with your label fit. Okay. The next example which I would like to take is that once you know that your structure is fine, so I will take this XRD data, the same structure, and I had a CIF file here, which I was generated in one of the previous experiments. So using this CIF file, how can we start create a PCR file? So I have this toolbar, edPCR. Okay, I will go to this. I will copy this destination. I edPCR. I can go to the CIF file to PCR conversion. I specify the PCR file, select that. Okay, it will give you this option. You will choose the radiation which you have. So this is X-ray data. We use X-rays. These are the cell parameters which are given in that CIF file. This is the space group which is specified in the CIF file. I say okay, and I can save this. So you can see that this PCR file is created with the same name. You can see this PCR file. The information it contains here is, once it has converted from CIF, I can show you a lot of things. So it is basically, by default, it goes into the pattern calculation. Okay, it's not showing the, it doesn't allow you to do the refinement. It will create a PCR file, which is for pattern simulation. Okay. So if you want to see, I can show you that how the pattern simulation works. Okay. So I can just call this file. And we can see how this simulated pattern looks like. Okay. So this simulation depends upon the background, basically 0. And since PCR was 1, it has actually overwritten this file. It's okay, we can modify that. But what it has done is that it has given you some idea of how to simulate a diffraction pattern using the information from the CIF file. And if you don't want to refine or index, you can actually get the peak positions and HKL values from the CIF file. And you can, if you can see, it will tell you the HKL values and the 2 theta position for that HKL value. So you can use this as for manually doing the indexing also. Okay. So now in this case, I want to do the refinement of the X-ray data. So I'll call it 0. And this is the X-ray radiations which is there. So it's fine with me. I don't want to override my PCR file. So I call it 2 so that it can generate the new file. And since I already have a curved data, okay, if you look at the XRD data, okay, so you can see that it is not a flat background, it's an angular background. Okay, so this is because at initial angles you have a lot of A scattering, which actually contributes and increases your background. Okay, so this can be put in background. So since it is not a straight background, I will not use polynomial, but I will actually would like to add the background points. So these are the background points which I already calculated and put. I can copy and paste it here. Since I'm not using this action, I can get rid of this part. Now, since I'm not using the profile, the polynomial function, I have to specify how many background points I'm actually using. So I have used 64 background points. I have to specify that. Now, one thing to remember and keep in mind is that the foolproof is, or WinPlotter is very sensitive to the format of the file. Okay, so this whatever is given as a comment or is hidden by this symbol is actually the program doesn't read that line. Okay, it is for our convenience that we know what are these numbers. Usually it looks into these lines and the numbers. Okay, so you should know what line and what is the parameter being given there. Okay. So now, okay, I can ask the program to automatically assign the numbers for refinement. So I can keep it 1. So make sure that PCR is 2 in all cases, whether it is label or refinement. If you want to get the analysis of your data, you can keep it 1. Okay. And you can specify the range of 2 theta. Okay, so this is actually 2 theta. So if you go to the instrumental background information, which I have actually put into something, I know these are my instrumental values. I can just copy and I can paste it here. Now this instrumental file is not available. Actually, I had created it and put all the information because this is what I'm going to use. This is the wavelength. This is the shape function of the instrument which I was using. So I'm using that peak shape function. Okay, and these are the HKL values, UW values for this instrument, which I have already, okay, which I can actually copy and paste here. Okay. So I paste it here. Right. So since it is, I'm trying to do label fit, I don't have to specify the number of atoms in the unit cell. Actually, I can make it 0. I have to tell the program to calculate the label fit. So I remove all this information which is not required. I can retain this scale factor. I can assign one scale factor, but I'm not going to define that scale factor. Okay, so I just leave it at that. And I have to specify what are the parameters I want to define. So I will define this values. Okay, I have already shown you the label fit. So I'll just go back and I will. Okay, now we can define the structures. Okay, so, sorry for that. If you don't know the ATZ values, so we can actually keep it 0 and let the program calculate depending on the occupancies which are given. Now, occupancies which I have given, which is from the set file, is same. Like if this is close to 0.5, this is 6 by 36 actually. So this is 0.1667, similar here, and this is close to 1. So my stoichiometry is like 3116. So which is same. Now I can refine my scale also because I'm going to refine the structure. And this is the where I can start. So I can specify the range. I want to see my PRF file. So I can refine, I can specify the range. And this is like 10 to 80 degrees, my 2 theta range. I can restrict to that one. Okay. So I think this is okay. We are all set. We can just start with the refinement. I can go back here, reset this, and I can ask the program to run PCR. Okay. Now, before we do that, you can actually specify the number of cycles it wants to run. So I say I want to run for. I want to run say for 20 cycles. I can actually retain the default values, or actually I can refine. I can reduce it to 1.1 so that it is more final. It can go into more iterative cycles. So I can specify this part. So when this is done, this is okay. This looks scattered, but it is more or less fine. So we are all set. We can actually start. I can show you this. Okay, I can start with this PCR file. And since I am using different PCR file name, I have to specify the data file name. So it says check your instrument parameter. Okay. So as I said, I'm using the instrument 10, but here it's by default takes instrument 0. So I have to correct this part. Okay. And I will ask the program to run this. Okay. Again, same cycle. So I have asked the program to do 20 cycles, 20 iterative cycles. So it will try to scale and also define the cell parameters. Okay, so it has not reached the conversion at this time. Okay, so first thing I can do is I can stop this. I'm not defining the cell parameters, I'm only defining the scale. Okay, so maybe I can increase the number of cycles, and maybe I can reduce it by 1 factor so that it converges faster. I will start again. So you can see that progressively it is actually calculating chi-square at the end of each cycle. So it is going to the number of cycles. Since it has not reached the minimum of the scale value, it is going to the next cycle values. Okay, next iterative cycle. Until it reaches a convergence, it will go on. Okay, since it has not reached the values, what I can do is that I will accept this values. So what I can do is, I can show you, you can keep an eye on what it's doing in the new file. So since we are asking one parameter to vary, it is varying the scale parameters. So this value looks fine to me. So what I can do is I can, instead of calling PCR file, I will call the new file, which is actually the new PCR file with the refined values. So before you do that, it will ask it gives you control on whether to overwrite the existing PCR files. I said okay. So it will overwrite the PCR file and then start the refinement cycles again using the new values. Okay, so at some point it should converge once it starts reaching the minimum value. Okay, so I can do that again. I can similarly do that. So it finishes all iterative cycles. At some point it converges and gives me this chi-square. So visibly my fit looks fine. It has fitted most of the back positions. The difference pattern is more or less small. Okay, there's small anisotropy in this sample because the small shift in the quick positions, which can be corrected by defining. So, okay, this is my last cycle value, defined value in the new file of this scale parameter. So next parameter which I can introduce to refine as a program is I can enable the refinement. Since it is a hexagonal structure, it is a hexagonal lattice, so I have to define the gamma also. This is a special condition for hexagonals. Otherwise, you define only the ABC values. In case of monoclinic, you define the beta values also. Okay. Now, the condition is that A equals to B in case of the hexagonal cell, and C is different. So this is what it is. So when I ask the program to assign the numbers on it, so it will automatically do that. If you have seen this old file. Okay, we will define this and I will show you that once we define that, it will automatically assign 2 and 3 to this values. So I can call this PCR new file again. And I can use that information, okay, and refine it further. So it improves my chi-square and it tries to improve my fit also. Okay, so like that you can refine it in next cycles also. Okay, and let us try to reach minimum and see how the values looks like. Okay. Okay. So if my starting value is slightly off from the ideal values, okay, so it will try to undergo that correction again and again, try to minimize the values and reach the convergence at some point. So yeah, I'm sure it will converge this time. Okay, fine. So if you see the program, it says convergence reached at this cycle, and these are the values, chi-square. And this is what the final fit you get. Okay. So you can see the intensities are matching, the difference pattern is small. Okay, since in case of X-rays, the spacing is 0.02 degrees. There will be points in between that. So there is always some, we cannot have a flat background. There are always some, you can say, disturbance in that. Okay. So because the data is spaced, actually it's not a continuous data, it's a spaced data. So this is the final value which we have got. We are using the same parameters, we are not defining anything. Since I can see that my chi-square is good, my fit is fine, so I can stick with this. So what we have done is that we have defined the scale parameters, we have defined the ABC values. What it does basically is that it fixes the position on the y-axis, and the cell parameters fixes the position on the x-axis. So my position of the brag peaks and the position of the pattern is fixed by these two parameters. So since my starting values are more or less ideal to the actual values, so it has converged with a reasonably good chi-square value and reasonably good fit. Okay. So next step which we can do in this exercise, okay, if you can see this, I had shown you that since I asked the program to automatically do that, it has given the codes for refinement according to that. If you don't want to do that, if you want to control which parameter to be defined first and which parameter will be defined later, I can put it to 0 and then I can manually give the refinement codes. Okay. So, okay. So next thing which we can do is that now I have the neutron diffraction data. Okay. I want to start with the neutron diffraction data. So I can use the file which was defined using the X-rays, and I will modify that file for the neutron diffraction data. Okay. So what I will do is I can come back here, and again using this program, now you know what are the instrumental parameters for this file. You can input make those changes, appropriate changes. So in this case, I'm using the pseudo-wide function for the interferometer. So I will change this part. So what will be different is the half edge will be different. The angular range will be different. So angular range has to be different. And of course, your wavelength has to be different. So okay, in case of neutrons, since it is monochromatic beam, we use only one wavelength. So it is monochromatic. I will make it 0, and I can make it 0 also. It doesn't matter. So I will change the peak shape function to 5, and this has to be 5. Okay, so I already have the structural information. What I need to change is the background. So for case of neutrons, okay, we can change. Okay, I can show you the data file also. So in this case, I'm using a different file format. So this is like starting angle, the step size, the end angle, and these are the points according which are spaced at each spacing from the starting angle point. So this is called 10-column format. So in case of foolproof, if you go back to the PCR file, then I have to specify what type of, if this is not the usual one, so I will make it 0. Now I have to specify the background positions because the X-rays and neutrons, the background positions will be different. Okay, so what I can do is I can go back here and I can call my data file. So I have to use the correct format now to call the data file format. Okay, so let's call this. Okay. Okay, just got. Okay, it has got stuck. Okay, let me close this and start over again. Okay, so when I call this data file, okay, I can actually, this is how my data looks like. So actually I can identify the background points, or I can actually ask the program to do this automatic background. I can, if the data is noisy, I can ask the program to calculate the background like according to that. Otherwise, I can store these points. I'll ask the program to save background points. Name it, give some name to that. Okay. And I'll edit, which means I can actually copy these files. And I can put it in my actual PCR file, which I'm going to use for the neutral diffraction data. Okay, so now I have 55 background points. I will save like that. Okay, so now we are ready. So we have the picture functions, and it's now actually job type has to be 1 because it is neutron data now. So we are using one phase refinement. The peak shape is defined, wavelength is given, the range is given, background points are defined. Okay, so now we are almost set. So we can ask the program to, again, we can start with the, since we are starting with the X-ray refined values, we can stop this value. And I will start with this scale again. So depending on the intensity of my data, the scale has to be different. So I will call the program. We'll see how the scale value behaves. Again, the file name I have to specify, and I ask the program to calculate that. So depending on this model, so the model structural model is same. I'm not changing the structural model. Only thing I'm changing is the data file and as the instrumental parameters associated with that data file. The same structural model can be used for X-ray data as well as for the neutron data. I have not changed anything. The only thing is that the information which I can refine using X-rays and neutrons are slightly different. So I can refine these values. Okay. You can see that, and you can actually, okay, this is the new file which is generated. I can actually see the PCR file, which was the initial file which it has taken for refinement. And it has actually done the calculations like that. So depending on that, I can refine the cell parameters again. And I can also refine the backgrounds. So if I specify this background points to be refined, I'm asking program to do the refinement, to assign the coefficients actually for refinement. So I can start again using some parameters which I have introduced for refinement, and it will do the refinement. And at some point of time, it should converge. Like that, it will go on, and at some point, depending on which parameters you're refining, it will converge. What I wanted to show you is, of course, this pattern is not completely fit. You have to work on that to get a proper fit by defining different parameters. Okay, so what I can do next is that I can define all the background parameters. I can define the positions. I can define the p-iso parameters. And since my stoichiometry looks fine, because I'm able to account for all intensities and all positions, I will not define the occupancies. But in case I'm looking for a cation distribution, if I don't know whether, like in case of spinels, you have A site and B site, and the atom can go on either of the sides. So in those cases, you have to do the occupancy defining. You can actually adjust it, like Dr. Babu showed yesterday, and you can adjust it and you can define those occupancies to get the correct composition, a cation distribution. Okay, so once you do that, what I wanted to show you is that you can go back to EDPCR and actually go to the refine. You can call the PCR file. Okay, and I wanted to add what is called as a bond balance information. I want the program to calculate the CIF file, and I want the program to do the calculations using the previous methods. So I have to enable that. Ask the program to calculate the geometrical calculations, which is bond length. So I have to specify some maximum distance, or you can give a maximum angle, and I have to specify how many cations and anions I have. So in this example, I have 3 cations and 1 anion. Okay, I will say OK. So program should save this. Save this for PCR file. It's exit from there. Now, if I open the PCR file, okay, so what it has done is it has added these lines. Okay, depending on the information we had asked, it has started from more. It has given these lines, and it has given 2 open lines for us to feed that information. I can give some tolerance, say 5% something, and I can specify the cations along the balance state. So I have calcium, which is 2 plus, I have cobalt, which is 2 plus, and manganese, which is 4 plus. And again, I have to specify oxygen, which is 2 minus. So I have specified 3 cations, I have specified 1 anion. So I have to tell the program which is the first species, second species, third species, and fourth species. Once I do that, again, when I use the EDPCR, it will always put it to 1. So I have to correct it every time whenever I use EDPCR and make it 2. Okay. So this, again, if I call the PCR file, it will do the refinement. Okay, it has gone through certain cycles, number of cycles, it has reached some point of calculation. But if you see the data files, you can see that it has calculated few files like PVS, it has calculated a CIF file. Okay, we have asked the program to generate a CIF file, and it has calculated distance files. It has calculated some other files also, which can be used in Vesta. So if I have installed Vesta, you can actually see your structure in Vesta. So this is how your structure looks like. Okay, this is a rhombohedral structure, R3/C, but it has a hexagonal setting. So if you can repeat this unit cell, you will get the hexagonal unit cell. Okay. So this I can stop. Similarly, you can use the FST or Full Studio to look at the structure. It's similar to what you see in this Vesta, but it doesn't show you the bond ends or bond angles because we did not ask it to do that. Once we ask the program to do that, you have to edit the FST file and ask the program to connect the bonds and bond ends. You can put it in the PCR file, and it can be done in the FST file also. You can edit it and you can do it. Okay. So what is the important part is that if you do the previous calculations, it tells you the bond valence sums for the 4 cations, for 4 ions which are there in the unit cell. It will tell you the GII index, which is a term which is used to quantify whether your refinement is going in the right directions or not. This is useful, or this is done mainly for the ionic bonds. In this case, we have cations and anions, so it is possible to do the bond valence for them. What another feature in this is that it calculates this distance file, which is basically the information about the bond distances between the different atoms. So it is the information which it has taken. So it shows you the distance between calcium on oxygen, calcium and manganese, calcium and cobalt. The bonds which is made by calcium surrounding it, it gives you the bond distance for that. Along with that, it also tells you the bond distances also, bond angles, sorry. It gives you the bond angles also. So it gives you a huge list, then calculates depending on the tolerance which you have, gives you a huge list. You have to pick the correct bond lengths, bond angles when you want to use it for your applications or for further processing actually. Okay, so this is how your PCR file looks like when you have this bond length and bond angle calculations embedded into that. Okay. This can be done externally by using bond star programs also. Okay. So now we can move on to the next example. So where I wanted to show you that how to identify an impurity phase and how to add a secondary phase. So if you look into the PCR file of this is a neutron diffraction data which was done on this lanthanum based compound with some substitution on that. So when you do the substitution, okay, in case of manganites, most of the people who work on manganites can relate to that. So now I have lanthanum, bismuth and strontium at this A site. So if you consider AbO3 perovskite, on the A side, I have lanthanum, bismuth and strontium. So the total occupancy of this site, so position for all the three atoms on this site has to be same. The thermal parameters is same because it is a statistical distribution. Okay, so it is in a unit cell you have all the three atoms which are statistically distributed at the site by this occupancy factors, which means in this case when it is 0.4, it is lanthanum 0.3, bismuth 0.4, bismuth 0.4, strontium 0.3, and so on. So in this case, you can see that lanthanum, strontium, and bismuth together they make 0.5. That is the full occupancy of this site. And similarly for manganese and oxygen, it is distributed according to the stoichiometry. So if you are substituting anything at any site, you know which site you are substituting. So you should substitute. You should place your ion or atom on the same site, and you have to distribute the occupancies according to the chemical composition. So this PCR file is relatively ready. I can just show you how it works. Okay. Maybe I can just define the cell parameters just to show you how it works. Okay, I just run this PCR file. So I call the PCR file, data file. I can run this. Okay, fine. So it has converged Hudson cycle. And now you can see that there is something which are not completely taken care of. Okay. Though the composition is fully stoichiometric, I am not able to define this part. So, and you can see that there's some extra peak coming here, something is not matching here. So you have, and something is missing somewhere here also. So some peaks are not actually accounted for. So what it means is that maybe I have an impurity secondary phase, okay, or some of the starting components have remained unreacted. So how to identify a secondary phase is the best way of doing that is that you know your starting composition, what are the elements you have taken. You would have taken lanthanum oxide, bismuth oxide, strontium carbonate, manganese oxide to prepare your compounds. So one of the suspects would be from this list only. So what you can do is, okay, so you can actually identify what would be the possible candidate which will have given rise to that anomaly. Okay, whether why it is not fitting, maybe because something has remained unreacted, which is not accounted for in the first phase. Okay, so one way of doing is that a very small slide. Once you identify the spacing for that position, okay, what we can generally do is okay, there's some databases which are available. You have to identify. So in this case, I identify that thing that it is MNO, which has remained unreacted, and I have used this is a presentation. I have used this ICSD database, which is available in PRC. So using that database, I know a certain set of compounds which are available, which can have possible positions to that. So what I will do is that I'll take the spacing for that peak, okay, and I'll try to get the positions for that. Okay. So this in 2 theta you can actually get it in these spacings. So I will try to match the unreacted peaks, the additional peaks in this spacing, and match with this database. Whichever matches closest to that, I will assume that is the compound which is can be the secondary phase. Okay, so I will download that zip file, and when I go to that zip file, it gives me a lot of information about the atomic positions and space group cell parameters for that phase and all that. Okay, so I can convert it into a PCR file, and I can use this PCR file to put it in my the phase, add it to the phase 1. So accordingly, okay, I can close this. Okay, so accordingly, I have prepared. You see, this is the PCR file which you can generate, convert from CIF to PCR. So this is the information which you can get. So from this PCR, what I can do is that I can copy this part, okay, and paste it as it is at the end of the first phase. So this becomes my first phase, and this becomes my second phase. So this is MN304, which I suspect is the culprit. So I can add this phase. Now what I have to ensure is that the instrumental parameters should be same. What can be different is this scale factor, because the scale will determine my phase fractions. So I can use a different scale factor for the second phase, and I can refine the cell parameters of both the phases and try to get the proper fit. Okay, so if you do that, so if I run the secondary phase, the program with the 2 phases, same, I can use the same data file. I have to do nothing with the data file. The same data file will work. Now you can observe that after adding the secondary phase, actually it has accounted for this anomaly. It has accounted for these extra peaks. It has accounted for some of these peak positions which were not accounted earlier. So, what it means is that there was some say deficiency, or there is a secondary phase which has come up during the synthesis process, and it can be accounted by. So I can find out what is the phase fraction of that. So how I do that is that I can go to the sum file, and at the end of the sum file, it just summarizes all the results, and at the end of the sum file, okay, it gives you the phase fraction for both the phases. So phase 1, phase 2, it tells me what is the phase fraction for phase 1, what is the phase fraction for phase 2. So I know that in this case, for this sample, there is about 3.5% of MN304 impurity in the or unreacted phase in this phase. So like that, if you have more than one impurity, you can have you can add up to 8 phases. So foolproof can the Winter or foolproof can take 8 phases at a time, and you can calculate that. So these phases can be impurity phase, secondary phases, it can be magnetic phases. So you can refine 8 phases at a time. That's the you can say the power of this program. Okay. The next one I wanted to show you is about the microstrain and microstructures. Okay, so before I go into the details of that, I can just want to show you what happens when you have a sample in which you have tried to reduce the particle size by some method. Okay, so what this is so this praseodymium bismuth strontium manganese oxide. What we have done is that we have used high energy planetary ball mill using the same sample, and we have tried to reduce the particle size by milling it for a certain amount of time. So this is my bulk sample, which was prepared by solid-state reaction method. And when I do the X-ray of that, this is the peak I get. And when I reduce the particle size by ball milling, I get this kind of broad. Okay. So now this broadness is firstly mainly because of the reduction in the particle size. And it can, because of the method in which the sample is prepared, you can prepare by chemical methods, solvent techniques, and so on. In this method, it is a brute force method. We are actually milling the sample for a very long time at a very high speed. So there will be a lot of stress built up in that. So there will be micro strain in this. There will be reduction in the particle size also. So our idea is to show you how to estimate the particle size and micro strain using foolproof. So if you look into this PCR file, for bulk sample, I don't have to do anything. I just want to calculate the particle size of the bulk sample, whatever it gives. So what I have to use is the instrument resolution file. I have to specify in the program that I have to create. I am going to supply a instrument resolution file in addition to the rest of the information. So when I have an IRF file, I can show you what IRF file of the format which I am using here consists of mainly the wavelength with the instrument basically peak share function which it uses and the half width parameters like UVW, X, Y, and Z. So when I use this instrument file, I can only define the instrument. I cannot define the instrument contribution, but I can define only the sample contribution, which is in U and Y. Okay, so when I do this, I can run this PCR file. Okay. Somewhere converge. Okay, so once I have done this, you can see the number of files it generates. It generates something called MIC, that is called the microstructure files. So when you look at the microstructure file, actually you can reduce this so that you can see everything in one slide. You can actually gives you a whole list for each peak back position. It calculates the apparent particle size, and at the end of it, it tells you what the particle size is. The units are in angstroms. Gives you an anisotropy of that. It also calculates the strain in the sample. Okay. So this is for the bulk sample. But when you go to the same I can do for the okay. Another thing what I can do is that since it is the same sample, what I can do is I can take this and I can put it in the same PCR file. Okay. I can use the same PCR file, but I have to change for the background of that point. So if I can use the same information, which is just there here, but I have to change the background because the data set is different. Okay. So instead of that, I will use this background. So number of background in this case is 15. I have already substituted that. So I'll put it here. Instead of 14, I will make it 15. Okay. The rest of the things should be same. So my composition should be same. My instrumental broadening should be same. Only the part which will change here is that the half widths, because the particle size is reduced, the strain, and probably the cell parameters may it would, because this data to data there will be small change. So there's small correction in the cell parameters I can do. So what I will do is I'll call this new file for the ball mill sample, and I will ask the program to run the refinement. Okay. So once it considers the background, it can actually, the only thing which I'm changing here is the cell parameters and the background points. I'm not refining the background, I just put the background points. If I refine the background points, I will get a better fit. Okay. Since it has not fit properly, it is giving this error message. Probably if I start refining the backgrounds, it will give me the point I wanted to show you after this refinement is that it also calculates the microstructure file, and you can, okay, since it has not done the refinement properly, it has not calculated the particle size. Okay, so what I can do is that instead of refining this, I will refine the background first. And put it, go back to the PCR file. I don't want to do in that file, so I will go this. And I will refine the background first. Okay, for the timing, I don't want to refine the cell. I will refine it later on. Okay, now let us see how the program goes. I'll refine the PCR file again. Okay, say some issues. So, okay, I can go back. Probably check the PCR. Okay, this is resolution limited. Okay, so what I will do, I can actually calculate the background points here again. Select the background. Try to avoid the back peaks when you select the background points. Calculation. Okay, to say the background. I will look at this file. Okay, let us see how it goes this time. Okay, what I'll do is not refine all these parameters. I'll just stick it to that. Let's just see how it behaves this time. Okay, so it has done some refinement. You can improve upon that. The point is, when you see the microstructure file, okay, it should have calculated all the HK positions. It should have calculated apparent particle size. It should have given you the strain and the particle size again. Okay. So now, since I have this refined values, I can again introduce this strain also, and I can refine the cell parameters again. And also, I can try to refine this half weights, the background positions also. And I can try to see how the refinement looks like after this. Okay, fine. So it has not converged, but fine. I can show you what difference it has made. Okay, so now you can see that it has calculated the particle size for the highest mill, I mean the nanoparticle sample, which is like, which was milled for about 240 minutes, like 4 hours. You can see the apparent particle size. So when you compare this with your bulk sample, you can see that it has reduced the particle size by a factor of 1, so by about 10. Okay, this is how you can actually work upon this, and you can actually calculate the particle size using this. Another thing is that particle size, in this case, we are assuming it to be the broadening is isotropic, but that may not be the case all the time. So it can have anisotropic broadening also. So in those cases, what you have to do is you have to supply what is known as the model, okay, size model, shape model. So it has special conditions. You can specify the peaks which actually are not matching, which you expect that either the peaks are shifting because of the strain or the reduction in the particle size, or is it that some of the HKLs, their half widths are changing more than the instrumental broadening or the sample, overall sample broadening. So some peaks or some planes may be shifting more than the other ones. So in those cases, you can do what is called the anisotropic broadening. So that PCL file is there. So I can just show you how it looks. Okay, that also gives roughly similar information, but the case is that if you see from isotropic broadening, if you consider it to be an anisotropic broadening, you can actually show how the anisotropic looks like. This fit compared to the isotropic broadening is much better than that. Okay, so if you look into the PCL file for this, or the MIC file for this, you can get the size of the particles for different planes are different. It calculates all that for each diffraction and gives you the average particle size as well as the strain. Okay, so though it looks similar to what we did with isotropic broadening or the normal broadening, when it is a non-linear broadening, then in those cases you can consider this anisotropic broadening, and you can actually get the particle size and strain from that by adding additional information which like this, depending on which size model you are trying to use and what strain model you are actually applying. So how many peaks you are referring, which have those reflections which can have shift in the Gaussian part, the Lorentzian part, or the half, the U parameter, which can be slightly different from the overall average picture. Okay. So these are the different things which you can do with the Rietveld analysis. And just a second, I will go back to my slide again. Okay, so with this, these are some of the information, the quite useful references which I find. Particularly if you're interested in finding out what are the R values and how important they are, you should go through these two papers. This is the books which Dr. Babu and Dr. Srivuri also mentioned, which are very useful, and particularly for powder diffraction and Rietveld method. And this is the manual actually written by one of the authors of full proof is Dr. Karwaha, Professor Karwaha, and he has written this very nice article. And there are, of course, there are a lot of literature available on the internet, and along with that, I think this will be quite useful. And with this, I would like to thank you for your time and attention. Thank you very much.
Thank you, Dr. Rietveld. There are several questions. So,
Yeah.
would you like to take for some time and then start answering the question, or what do you suggest?
Yeah, we can do that, but you have to help me and get back to normal mode. And I think it's presentation.
So we can I put the questions?
Yeah, just give me a second and have.
Okay, sure.
Yeah, please go on.
Okay. So there are several questions. So first question is why the intensity associated with any peak changes with doping or of impurity atom?
Yeah, so the intensity also, if you see the structure factor equation, the intensity depends upon the scattering factor of the element or the atom, which is contributing to that scattering. So if you replace a high scattering element or high Z element with a low Z element, the scattering definitely will come down. So that will affect your intensities also.
Okay. So if data quality is not good, if we refine only B iso, not B of each atom and put 0 or 1, is it okay?
Can you repeat that, please?
Basically, they are asking whether if data quality is not good, then B iso and can be refined rather than B iso for each atom.
Yeah, if data quality is not good, I would suggest not to play with 3i, so it can give rise to false minima and negative results. So you should go with the standard values which is reported, or for that compound or isostructural compounds, or for particular atom in similar crystallographic structures. And if data quality is not so good, I think it's better not to fiddle with that.
And what is the significance of specifically using Bragg-Barentano geometry for XRD data and Debye-Scherer geometry for ND data?
Yeah, the X-rays we have seen that it cannot penetrate deep into the matter. Okay, it actually uses the reflectance, works on the reflectance geometry, it cannot go deeper in that. So you basically work with top layer or 1 or 2 layers below that. Okay, so X-rays are restricted to reflectance only. Whereas in case of neutrons, X-rays again being scattered by electrons. So it starts, the moment it tries to enter this sample, it gets reflected by that or deflected by that. The neutrons being chargeless can penetrate deep into the matter. Okay, it does not look into the electron cloud, it interacts with the nucleus. If you are talking about the structural part, okay. So it gets scattered because of the nuclear energy levels. So it has to work more with the transmission geometry than the reflectance geometry.
Okay. And how the scattering amplitude remains linear with 2 theta?
In case of neutrons?
And in case of, I think, X-ray?
The scattering amplitude decreases with as a function of 2 theta, because the scattering amplitude is depends on the scattering angle also, right? You go away from the direct beam, actually the less intensity it will show.
And how should one decide on which Wyckoff position the atom should be placed for a new material? Is it just hit and trial? This is, I think, very common question. People are little confused regarding this refinement.
Yeah. The point is that in Rietveld refinement, we are actually refining a model. So if you take a model and you can place your atoms according to that model, but if you are working on a completely new material which has no precedence, then you have to look. First of all, is identify the space group. What are the positions which are allowed by the space group? Then you have to work out the structure factor, which element will scatter which reflections. Depending on that, the systematic absences and HKL conditions, you have to determine which atom will go to which Wyckoff position, which will contribute to those HKLs. So it is a very tedious process. It is not a simple one. There are certain programs, so foolproof also does that simulated annealing kind of direct methods, but it is not very straightforward. So best thing would be to run a known sample, try to see if you can get a correct answer for that known sample, then to implement it on an unknown sample.
Will step size in X-ray diffraction, the crystallized size will be affected or not?
The
step size of X-ray will affect the crystal size.
Okay, it is like this. The step size will affect your resolution of the X-rays, of your resolution of your XRD data, but that's an instrumental characteristic. The particle size, it depends on your sample. If the instrument is able to detect the broadness of the peak, it can calculate your particle size. Okay, so the resolution has limit, okay, but the instrumental function like U, X, and Y has a contribution from sample also. So if you can able to define the instrumental functions, anything up beyond that, it has to be from the sample. So yes, it can, but the instrumental resolution will not affect the particle size like that. It's
there is one more common question that the chi-square value, if it is less than 1, it is acceptable.
No, because in that case, R expected is less than is more than RWP. Okay, so RWP cannot be less than R expected. The R expected can either be equal to RWP or it has to be less than that.
And what to do if same peaks are Rietveld fitted with more than one structure and space groups?
Yeah, so the structure, you can have only one unique solution for a structure, but in case of a structural model, okay, there may be small discrepancies, small changes within these crystal structures, right? There's very few examples like R3 versus space group in a rhomboidal structure or hexagonal setting is very close in terms of diffraction peaks to a monoclinic structure like C2 by C. But you have to see which of these two space group will match perfectly with your sample, right? It has to see, you have to see that it doesn't generate any additional peak positions. It should account for all the bragg peak positions. Intensity also should match. Okay. So it is very rare that you have same data set matching to different space groups. It has some conditions have to change in that.
And there's one more common question: is how to get the instrument parameters.
Yeah, you have to run a standard sample. A standard sample is something for which the parameters are already known, like cell parameters, and the instrumental function is already known. So once you run the standard parameters, you can fix the cell parameter, the ABC values. You can define the half widths, and you can get the instrumental resolution file. Not from your sample, but from a standard sample whose parameters are already known.
And why there is a negative?
Yeah, usually the X-rays you have this NIST standards which come with the X-ray instruments. For neutrons, we have our own standards which we use for calibrating the data.
Yeah. And why there is a negative scattering length for titanium and manganese, Mn in this case, in the case of neutrons?
Yeah, so this negative scattering length actually is the in phase or out of phase scattering length. Okay, for in phase scatterings, it is positive. For the phases which is 180 degree apart or phase shifted, that is negative scattering. Okay, it's a convention which is used. So why it is positive and negative is that because of the energy levels. Okay, for each nuclei has a different reaction to the neutrons. So depending on that, you can have scattering lengths. It has nothing to do with the diffraction as such.
And one more common question is: can Rietveld refinement be done on the thin films?
No, it is a powder diffraction method used for powder samples. So thin films will not give you any information. It is not useful.
So one more question is this: does in parasite type structure it is necessary to refine the alpha, beta, gamma? I think it depends upon the compound.
Okay, it depends upon the symmetry of the system, right? Alpha, beta, gamma is restricted by the symmetry or the space group, right? Only for monoclinic or triclinic, you have the option of refining the beta or alpha, beta, gamma. Okay, but in not all cases you can refine alpha, beta, gamma. It is restricted by the symmetry.
And there was more confusion about the doping consideration. I mean, like one question is that in case of doping, can I insert the dopant in designated site? But in case of intercalation and getting, where do I insert the intercalant? So this is confusion between intercalation and doping.
Okay. So the point is that if it is intercalated, it is somewhere in between the sites. It's not sitting at a crystallographic site. This reflection comes from the planes which are from those crystallographically different sites. Somewhere in between, if it contributes to the diffraction, okay, then you have to, it has to have a certain position, whether it is within the lattice or it is outside the same lattice. So if in a diffraction pattern, if you have more than one phase, you can identify what is the first phase contribution, what is the second phase contribution, right? But if it is a dopant which is not going with the lattice, if it is scattering, it means it is remaining as a secondary phase, which is contributing to the diffraction pattern. But if you don't see an additional peak from that dopant, means it is going to some of the sites where it is like it is a substitution at some of the sites. So like in case example I showed that lanthanum and bismuth and strontium are the same site. So it is statistically distributed. So lanthanum, bismuth and strontium will scatter according to their scattering length and as per the structure factor for each site, each position. So if it is intercalated, it has to be either it will not participate in this scattering process, or if it scatters, it is not part of the mean structure, it has to be the secondary phase.
And there's one more question is for preferential orientation sample, what input parameter has to be given for the refinement?
Okay, actually you can start with your refinement considering from 0. It should be ideally 0. But when you start using a preferred orientation model, or you can, there are 2-3 models which are available in foolproof. But ideally, it should be 0. If there is a certain peak which is intensity is increasing, or certain peaks whose intensity is more than the calculated intensity, then in those cases you can actually apply the model. You can define, there are PR1, PR2, PR3. You can define the direction, in which direction you want the plane to be, or that which plane it is preferred oriented, in which direction it is oriented. And then you can define the parameter which will actually apply to that particular orientation, particular peak, and try to fit that.
Okay, and one more common question was that how to make the PCR file using EDPCR. So that is very common. I think those who have
I showed you how to use EDPCR. Oh, I did not show that. Okay, but you can always try that. No problem.
Yeah, but if people have downloaded the foolproof, then they can go for the example file, and then there are different.
They can see. Point is, if you have to collect 2 points, 2 things. One is the structural information. One is the instrumental background, instrumental file. And if you can once you have got that data, you can get the background file, keep it ready, and you can start from file new in EDPCR and try to add phase by phase. Okay, maybe I can show in a minute if I can show you something.
Yeah, sure.
So you can start with a new. So once you ask for a new file, it will enable all these options. You can start from general. Okay, you can add. It gives an option of what you want to do. If you want to refine or calculate a powder diffraction profile, refine a single crystal data or integrated intensity data. That is like Rietveld method. If you want to do simulated annealing and so on. So there are so many options, and it will, depending on your choice, it will optimize for that. Okay. Similarly, you can add phases. How many phases for phase 1, phase 2? You can add individually, one by one. And then you can add for each phase. You can add information. What type of you want to do? Whether it is a structural model, you want to do magnetic refinement, you want to do with spherical harmonics of a magnetic model, and so on. Okay. So you can go through all this steps by steps. You can do the refinement. You can actually add the background file here. You can add the atoms. Okay, you can enable how many atoms are there in the structure. According to you can do that. Okay, so there you can go through all these points, and at the end you have to save this so that it saves as a PCR file. And you can edit it, and you can edit it using EDPCR. You can edit it using the text editor which I was using in this presentation. Yeah.
So I think this is all for the time being, because this is an unending process which we can continue till days and days. So okay. I request, if you have any specific question, you can write to the speakers, individual speaker, any of the speakers. Now I think we can move on the second talk of the day. So I now request Dr. N.P. Lalla, our colleague from IISc Indore, to speak on Rietveld refinement of low temperature X-ray diffraction data used for the structural tutorial studies in the perovskite and spinel oxide compounds. Dr. Lalla.
लाला जी अनम्यूट कर दीजिए, आपने म्यूट करके रखा है।
अभी ऑडिबल है शर्मा जी? हेलो।
Now we are audible.
Yeah, we need to meet. Okay. Before Dr. Lalla starts, I will be introducing. And Dr. Lalla is a senior faculty at CSR Indore Center, and he has been instrumental in making a high field, low temperature X-ray diffraction facility, which is unique in India. He will be talking on X-ray diffraction on some oxide samples, and this, I ask Dr. Lalla to start his presentation.
Thank you, Rajiv, for this nice introduction. So before I start, I would like to thank our director, Executive Director, Dr. Sriguri, to include me in this program. And so I am also listening to this whole lecture. So I am also listening to the lecture. So all my colleagues have delivered regarding equal refinement is marvelous, and I don't feel adding anything to that. Of course, we also do equal refinement very frequently on this, but I will not be adding anything to it. Since I have been listening all the lectures and some comments and some questionnaires from the audience, so I thought to touch both points. Yesterday there was someone was interested in knowing the anisotropic safe effect. And, so I have just added this, and since I have to explain this anisotropic effect, so I will be just talking something about the lattice concept. So most of my lecture, most of the part, will be related with the fundamental of stress pattern. And of course, since we do ritual refinement and we use for studying various perovskite materials and recently on spinel oxide, I one of the scholars. So I'll be just adding a few of the results. It's not something very involved lecture on ritual refinement and those things. We'll be mostly covering basics. What will be something new is a history about the X-ray diffraction, which of course people know. But most of the people know till the Ranjan who discovered the X-ray, and of course about this law diffraction. So I will just adding something extra to this, and then I will be doing presenting some of the results which I have obtained in refinement. So I'll just go to the next slide.
Balaji, small session.
Yeah, tell me what is session.
Balaji, वो माइक है ना माउथ के पास ले जाइए तो क्लियर रहेगा. आपका बात कट हो रहा है.
अभी क्लियर आ रहा है?
Now it is clear.
Pointer.
So this next slide actually shows you the position of X-ray in the electromagnetic spectrum. So X-ray we use is around the length of the X-ray is around 1 angstrom, and on the lower diagram basically so the characteristic and continuous X-ray we get usually from uncontrolled machines that in the lab. Oh, so this and welcome. Okay, so he started working on X-ray. Basically, his plan in those days, in 1890, people were working. Most of the people were working on negative rays, and perhaps his plan was also to work on negative rays. But what he found, new rays. Negative ray is nothing but the cathode rays coming from the vacuum discharge tube. So his plans were also to work on that only. But then suddenly found that some unknown ray was exposing to photographic films. They kept quite away from the instrument, and the cells were basically coated by beryllium cyanide, and then it is, and then only discovered that is something going all the way to long distance without getting absorbed and affecting the photographic film kept quite far from them. And that X-ray was later used in X-ray diffraction, and that was first proposed by Max von Laue. Now the discovery of X-ray diffraction also has a brief history. Max von Laue is basically a theoretical person, and basically he did his work with Max Planck, working in quantum theory of radiation. And although he was aware of many critical aspects of the symmetry, so one day basically one of his junior colleagues, his name was P.P. Award, he had to visit him regarding clearing some of his doubts regarding this person in periodic media, because all this, although diffraction didn't took place.
आपको थोड़ा जोर से बोलना पड़ेगा। इधर आ जाए, इधर आ जाए।
Okay, sorry. Some interruption due to the earphone. So now I think I will be better audible. So during discussion between P.P. Award and Max von Laue, Max von Laue came to know that the expected periodic distance, people were expecting that the solid line arrangement, periodic arrangement of atoms inside the solid. So basically, really came to know that the atoms are within the angstrom. Immediately proposed the experiment, and that was taken by some of the. He was theorist only, so it was taken by some of the experimentally known Nipping and Frederick, who were basically working there in the Munich itself. And the first experiment they did just the transmission through a crystal with the title of their experiment. And they found a very broad and some spotted picture in the see here. And then they improved the setup. Frederick and Philip improved the setup. And then they were second experiment were done in gene plant. And this is a photograph taken along 1 taking the structure. And this photograph has been taken along the of the structure. So the theory of this diffraction was given by Laue, but the next person made it more popular, the Bragg. And there were two Braggs involved in this, the father Bragg and son Bragg. The father Bragg basically developed the diffractometer. In fact, he was himself working on this corpuscular theory of X-rays. And so, but his son was involved in making this Laue condition more simply and more simple, and he gave the most famous equation of 2D sin theta to n lambda. So, X-ray was discovered in 1889 around, and of course, the Nobel Prize was in 1901. The theory of X-ray diffraction was discovered, or diffraction was realized in 1912. But we surprised crystallography symmetry, assuming that solids will be made of periodic arrangement of atoms. So all the theory about symmetry was discovered long back by some person Hessel in 1830s. You can imagine almost more than 90 years earlier, all theories about the 32 point were all available to the researchers. Where we were at this was the story about the discoverer who did the first diffraction experiment in India. So this credit goes to Professor Banerjee, who did the very first experiment in 1924, when only few such success had been determined from the world. and he worked on naphthalene and anthracene, and developing his own instrument was able to solve this structure. And later he joined WS Brand and developed the direct theory of the human crystal structure. The other person who contributed a lot in this field, and which he is still known, is Professor G.L. Ramchandran Brand, very famous chemistry. So he has also contributed so much in the so what people are doing before the diffraction was not known. Natural crystals were available. So this geograph tells that those times people are just looking at studying the geometry using contact crystal, just measuring angle between different particular crystal. So that year was 1780. Long, very less. So this just shows how the X-ray is generated. So this is basically the Coolidge internal design of the Coolidge tube. There is a filament of tungsten, and the current is passed through this. Some thermonic electrons are ejected, and they are accelerated towards the target, cooled, and then and this just in theory how they are generated. If you actually bombard falls on some KK level, the innermost level of the atom, then they are ejected out of the atom, and the electron from the higher level, they jump right to fill it, and therefore the energy difference is limited in the form of statistic X-ray. But almost 90% of the electrons falling on the target, they are used to make the continuous X-ray, and that takes and that happens by stopping the whole energy, converting the whole kinetic energy into a band of X-ray using simple electrodynamics. This was the method of modern method. This is synchrotron radiation, when the electron beam is circulating a closed loop, and whenever they are allowed to pass through a magnetic field, they get accelerated towards centripetal acceleration takes place. So we know that wherever a charged particle is accelerated or deaccelerated, like in the case of continuous radiation, if they are getting Coolidge tube, so they will emit radiation. That takes place in the bending magnet under the synchrotron source. So there we get a continuous radiation, very high intensity, and that high intensity is used in various types of experiments. The hard X-ray regime of that band is used for the X-ray diffraction studies. So this geograph shows this is a simple crystal. So basically, crystal decline materials are periodic arrangement in 3 dimensions of unit cells, and so even this knowledge about the unit cell and Bragg lattice are all known in 1850, much earlier the discovery of the X-ray diffraction. So these are the geograph shows the about the internal plane of a crystal. So basically, all periodic arrangements in the solid can be converted in the concept of planes, which are basically given by the Miller, and all of them can be indexed. So any plane in the 3D geometry, equation of plane is given by the intercepts. So if A, B, C are the intercepts on the X, Y, Z coordinate respectively, then the equation of the plane can be given by X by A or Y by B, Z by C equal to 1. So here the intercept is basically converted as the indices, like H equal to 1 by A, A equal to 1 by B, and L equal to 1 by C, and this acts as a tool to index. Indexing nothing but getting acquainted with a crystal system. So whenever you deal with a crystalline phase, the first requirement is to index the all diffraction peaks. So those indices are nothing but those peaks, indexing those peaks, and those things correspond to a particular set of plane. Okay, so I'll just pass this. So this shows that if you have a infinitely large periodic structure, so these black dot points are nothing but the lattice points, or you can take any specific periodically. So in principle, you can select infinite set of plane. For example, I have tried in the green line, basically representing the 1, 0, 0 plane. Similarly, the blue lines are representing 3, 1, 0 plane, and the red line is representing 1, 0, 0 plane. So someone can say that, okay, if you draw a line this way, that will basically index as 0, 1, 0 plane in a 2 dimension. So one can always think such a infinite set of such indices of 3 numbers, and all of them will be in principle present there. Whether we are able to see in a diffraction experiment or not, it's a matter of detail. That will depend on the parameter, and most of the time we cannot see all of them. So if a radiation falls on such a periodic arrangement, then using the Bragg's law, so we can show that we'll get a diffracted beam in certain direction. So for the condition is given by this equation 2D sin N lambda, which is basically a metrical form of the diffraction 2D sin theta, and I think it then give a vectorial form. So this equation k capital K equal to k minus k0 gives a vectorial form of the same equation, which is basically given by EPA model. So what we see here that a wavy pattern is coming here, which is basically nothing but an incident wave, and after interacting with this atom, it's getting scattered. So all scattering events, whether you are doing diffraction or not, whether impression intersection or not, this will give automatically a phase shift in all the rays. For example, in X-ray there will be 90 degree phase shift if the scattering is taking place. So similarly, somebody just was asking about the negative scattering length in neutrons. So basically, it's the individual interaction of the nucleus and the neutron. Here is an individual interaction between the atom or even the electrons in the atom. And so these phase shifts, since all these phase shifts is constant for all the atoms, most of the time we don't talk about this phase difference. What we talk about the geometrical phase difference is basically comes due to the path difference. Because path difference between this plane and this plane will be nothing but the 2D sin theta, and if this 2D sin theta, because if the rays, this angle is theta, this angle is theta, then this path difference will be 2D sin theta. If this 2D sin theta is equal to the integral multiple of wavelength u, then the interference will be constructed. So the whole diffraction phase is based on the scattering and the interference. So this shows the same thing, but in a simple way. So the green lines are representing planes, the parallel, and the interparallel is D1 0, basically showing that the planes are extended in 1 0 direction. And the blue line is coming from the left side going to right side, showing the Bragg scattering. So this part, the biograph is particularly for the students. Most of the time we talk say 2D sin theta to lambda, and whenever we are told to just discuss about diffraction and interference, we say 2D sin theta to n lambda. But nowhere is n, is nothing but the integer, is used in any calculation. Why this is? This is a question for the students, and I will try to answer. So we just miss this, replace this all n with 1. So why? So if divide this n, rewrite this 2D sin theta n lambda as 2D d by n sin theta n lambda, then we can say that any nth interference pattern P can be, so you will explain this, that this nth maxima is coming due to diffraction due to this D1 plane, the scattering from D1 plane. If you have divided this n and made it d by n, then you will say that this is coming due to a interplanetary spacing which is d by n, and for that n is equal to 1. Similarly, if the n is 2, then you can say that, okay, initially for D100, the difference was of second order, but for D1/2, it is the first order. So what it tells that all diffraction peaks in XRD pattern, we treat this as a first order diffraction, and therefore we can always escape is n and making it 1. The other important concept which is needed is to understand the geometry of diffraction, and most of the things we will be talking, because the anisotropy effect needs to the explanation of that needs to some knowledge about this wall construction. So this was given by PP award. I already discussed you that diffraction, the idea of diffraction to law came during the discussion with PP award. They were discussing during the lunch time, and that was the time was taken by the PP award to discuss some of the physical aspects of discussion in periodic media. So during discussion, this idea just came to the mind of Darwin, and he tried it and got the diffraction physics, diffraction excellence. So when that paper was published, that time he was still doing his PhD award, and immediately he happened to recall all his discussion, and then suddenly he just in his mind came that okay, we can convert all the diffraction phenomena.
Lalaji, can you stop? Since audio is not clear, we will make some arrangements. So just wait for 5 minutes.
I will make some. Whoever computer, I will make some other present.
Use my laptop, I will make arrangement for you. But his slide email
Vishwanath? Vishwanath?
Yeah, Dr. Rajiv.
Can you make a presenter? Okay, okay. Rajamani.
Rajamani?
Yeah.
Okay.
So Lalaji will give presentation from his laptop.
Done. Please tell him to mic switch on the mic. Please tell him to.
Roads and upgraded, trains suspended, heavy rains for life out of there in Mumbai.
Sharma ji?
Yeah, your mic is on. It is coming now.
Okay.
So I say voice clear.
Okay. So
Yeah, voice also clear.
not opening this PowerPoint.
Dr. Rajamani, voice also clear. Please tell him to start.
नहीं, ये एक मिनट, इसमें माइक है। ओके, उसमें पॉइंटर नहीं आ रहा है। ओके, आवाज आ रहा है? आवाज आ रहा है सर?
It is clear, Dr. Rajamani.
Okay, you can use this.
Then we can start now.
Yeah, you tell Dr. Lalla to start.
हाँ, शर्मा जी मेरी आवाज आ रही है?
हाँ आ रही है सर, बहुत अच्छा आ रही है।
Okay, ठीक है. So let me continue again. I'm sorry to the audience that there was some disturbance. So I will just come to the slide where I was just speaking. And okay, so I was just speaking to up to this slide. So you can always discuss any powder pattern taking n as 1, because we'll treat that every peak is coming due to the first order diffraction. So this concept of evolved construction, basically, just 1 second. ये पॉइंट हो गया। थैंक यू। Okay, so while looking at the paper by the Nipping and this Lowe, immediately recalled all in their discussion, and he could make out this geometry, that how a diffraction pattern can be expressed in terms of reciprocal space. So basically, he treated the incident rays as a k vector 0, which magnitude is given by 1 over lambda, and the scattered rays in our, it is nothing but an inelastic scattering experiment. So lambda will remain same. So the scattered rays will also, scattered in direction will also be have the same vector magnitude wise. So the G, which we say that this G is basically property of the material, and that the G vector is due to the periodicity into the material. What it tells that whenever a back condition is satisfied, the tip of a vector whose length is 1 over d. So basically, you can take this vector 0 to q1, which length is 1 over d1. Similarly, there is another vector q2, the length is 1 over d2, and third vector d3. So you can see that if you arrange all such vectors from the material originating from a fixed origin, then they lie on a circle. So that's what he make out from his own derivation, and this became famous as the evolved construction. So the radius of this sphere is nothing but 1 over lambda, and the vector of this length of these vectors is 1 over d. So it tells, and this concept is basically used to convert a given crystal into its reciprocal. So if you consider 1 d spacing in a given crystal, the pink lines, parallel lines are basically the set of planes. So the corresponding Q vector or G vector will be nothing but 1 over D, and the direction will be perpendicular to this vector. So now we'll just take a square lattice where all the green points are the lattice points in direct space, for example, which you can measure in angstroms or microns or millimeter. In this space, they are arranged in a square lattice. So suppose now we want to convert this in reciprocal. So you can select any random point in this or outside this. So I have taken O as a point to become as an origin. Then I can draw a line perpendicular to this because I want to convert this set of plane into reciprocal. And so D spacing is D100. So the vector length of vector will be G1 upon D100. So where to put this point? This is purely up to us, what scale you follow. So you can just make a scale. Let's suppose this D is 2 angstrom, then 1 upon D will be 0.5 angstrom. So you can say that, okay, I will consider 0.5 angstrom as my scale. 0.5 angstrom is equal to 1 centimeter as my scale. And at 1 centimeter, I'll put 1 point here. So this arrow will represent the reciprocal lattice vector for this whole set of planes which you are able to see here, all horizontal black lines. Okay, then one can say, no, I have another D spacing, half of this. That is always possible. You can set your crystal to diffract from this set of plane D200, which happens to be parallel to the D100, and the D spacing is just half. So naturally, 1 upon D will be just double of this, and you'll be getting G200. And the same way, you can keep making the reciprocal lattice vectors 300, 400. But somebody can think, no, let's select this other set of planes, which is basically represented by vertical black lines in the same lattice, and then we'll be able to get the reciprocal vectors like 010, 020, 030, 040. And then somebody can say that, no, let us take these oblique lines as the plane in the same lattice. You can see the green points are exactly same, but now we have selected this 110 plane direction as the plane. So here also you can get G100 to G200. So this way you can keep selecting different set of planes in the same lattice and giving them different names. You just remove the whole lattice, the physical lattice, and what will be end up with a reciprocal lattice plane. And what is important here, there is no need to search all the points. What is important to know, to search this the basic reciprocal vectors G100 and G010 in the 2-dimensional space. In 3 dimensions, there will be another plus 001. And once you know this, then you can make the whole lattice using this simple equation where H, K, L is basically the indices of the plane. So they're all integers which can run from -infinity to +infinity. So that way you'll be able to construct the whole reciprocal lattice geometrically. But the reciprocal lattice is not just a geometrical set of points. The property of such a reciprocal lattice is that all symmetry which this direct lattice has is inherent in this. So other requirement of this reciprocal lattice is the phase factor or the amplitude factor associated with each lattice point. I will just skip this. So in the actual lattice point, what we'll find, each lattice point will have a amplitude for this F00. You are aware about this capital F. It's a summation over Fi into exponential minus 2 pi I. Basically, it gives the form fact, unit cell scattering factor. So, for example, 001 plane, the unit cell scattering factor will be given by this. So, I have denoted it with very fade points. It means the scattered amplitude corresponding to this reciprocal lattice point is very weak. On the contrary, associated, the one which is associated with 110 is very strong. The 110 is slightly lower. So this way, in reciprocal space, we'll have geometrical arrangement of periodic points in 3 dimensions, and associated with each point there will be a scattered amplitude. When they happen to touch a reciprocal world plane, so now we have just done a small experiment. This yellow one is a crystal, and by definition, its reciprocal lattice point will lie at the intersection point of this incident beam, or this horizontal magenta line running is the incident beam, which is cutting this Rietveld sphere at this point O. So by definition of the Rietveld construction, the origin of the focal lattice point has to match it at this point. So if this is the orientation of your crystal, and this happens to be the origin where the focal lattice point is lying, the orientation of this focal lattice point will exactly be parallel to this direct crystal orientation. So if you will orient this, so if you will translate this, this will remain here only, because the focal space is invariant under translation. But if you will orient or tilt this, they will tilt. So I have deliberately made this geometry, this diagram in such a way that none of the points would touch. So in fact, if you are doing an experiment with a single crystal and your radiation happens to be highly monochromatic, and if you randomly put your crystal in the beam, you will hardly see any diffraction, because most of the time they may not touch any of the focal lattice point, and therefore to see the diffraction you have to tilt it. So what you have done, you have tilted the crystal by putting on a small goniometer, and you happen to tilt in such a way that this point touches this. Even no sooner it touches, there will be diffracted beam going on. It means we happen to satisfy a Bragg condition for this example 2. So this is nothing but 2 to 2. The focal lattice point has now touched it, so there will be diffraction taking place corresponding to this. So in fact, you can oscillate this crystal continuously. So one time or other, all the focal lattice point will pass through this, and they will diffract. And that is the method which they would oscillating crystal setup gives. It's a very old setup they have been doing. So the other thing regarding after geometry is the intensity associated with the focal lattice point, which is nothing, which is a square of the initial structure factor f square. So how to know about that intensity? So if a plane parallel X-ray falls on a crystal or any solid, I have just taken a random set of points. The green points are nothing but the atoms here, and a plane wave of X-ray is falling. Plane wave I have taken because the diffraction, X-ray diffraction basically follows the Fraunhofer geometry of the diffraction. So if a plane wave is falling, and just follow one of the rays which is going here. So if it is getting scattered from this point, from the example, this ray is getting scattered. So in the first scattering, you can see this is very intense circular point. So they will act. This will act as a hygiene wavelets of the X-rays of the same wavelength. So this scattered radiation will again hit this second atom here, and that will also scatter. And this scattered will again hit the third point here, that will also scatter. So you can see a first time a scattered radiation will travel all the through the solid and will scatter from each atom. So that way, every primary scattering from every atom in this collection will scatter. So there will be a secondary scattering, secondary scattering. So no one can stop this event taking place. So what it gives a picture that dealing with the intensity of a scattering is really very, very tough. So basically people started devising, and they reached up a theory, which is known as kinematical theory. So it has some considerations that I will just show in the next slide. But truly speaking, even a tiny nanocrystal, actually this event is taking place, and what we are dealing with all these theory, which basically, fortunately, it gives almost 98% correct results, is a kinematical theory where there is a huge approximation. So I just like to introduce you. I think most of you might be knowing already. I'm just trying to recall it. And so if in actual, so if you deal with this event, that you consider every scattered and re-scattered and re-scattered, then you will come up with a theory which is basically known as dynamical scattering. So every crystal, this event is taking place, even a tiniest case, but still a simple kinematical theory gives you nice pattern, a nice intensity, almost 98% matching. So how this so happens, and what is the limitation of that? I am all talking this from a book from Warren. It's a very good book for X-ray diffraction. So I think everyone should consult that. I mean, there are many books. I have just read it from there. So if actual dynamical scattering is taking place and you happen to satisfy Bragg condition, so if a beam is falling onto the crystal, this magenta volume is showing a very nice single crystal. What will happen? No sooner it touches the surface, some fraction will get scattered, and then that much intensity can be subtracted from that. Then most of the other intensity will be touching other layers, and they will keep diffracting. They will keep diffracting. So even if you consider that the physical absorption that we deal with the coefficient alpha is I is equal to I0 into exponential minus alpha x. So that alpha x, that alpha, if you consider that this volume which is showing in magenta is 0, even then just a simple diffraction event will make this intensity keep on decreasing 0. And after a certain distance, this will become 0. So we define this distance as a term known as the extinction distance, because your incident beam has got fully extinct by traveling this much distance. So for example, very high quality germanium and silicon, this distance comes into around 50 to 60 microns. So if you have a crystal, the highly perfect crystal of germanium silicon, and suppose if you are doing it, okay, so let me just say this, that this extinction distance will be different for different vectors. For example, this Xi equal to for the vector G, so maybe you can say G100. So for G100, this distance will be different. For G11, this distance will be different. So for germanium and silicon 111, this distance happens to be around 50 to 60 micron. So if you have a crystal of 50 to 60 micron, then whatever intensity is falling onto this, all of them will get scattered. So if they are not getting absorbed, even if they're not getting absorbed, all of them will get scattered, and I0 will become 0. But this distance is very large, 50 to 60 micron. So if you are doing a powder scattering using a single crystal of silicon or germanium, where particle size is crystallite size is 50 to 60 micron, your intensity calculation, which will be dealing with this kinematical, will be all wrong. That's what I want to say. It will be all wrong. They will be true, very correctly matching only when your crystallite size is much, so only below 5 micron or maybe 1 or 2 micron, they will be very perfectly matching. So this green volume is showing that if in such a high quality crystal is having, and if you want to get rid of dynamical scattering, then you'll have to make that crystal very, very small. And we are very fortunate, I will say you, that all of whatever materials we make, the size of the currently scattering volume is very, very small. Even the one which you say that it's a 10 micron size crystal, the actual volume which is scattering currently, that may be less than 50 to around 100 to 200 nanometer, not 1 micron. So what it tells that if your crystallite size is less than much less than the extinction distance for that material. So here I will give an example of silicon. Suppose it's the barium titanate. So if you can make a high quality barium titanate, one have to calculate for different G, what will be the extinction distance. If that particle or the crystallite size happens to be of that order, then all this calculation which you do, that will not be correct. Then one will have to develop theory for our theory is already there, sorry. So this kinematical theory will not work for that. So according to that theory, what it tells that incident I0 will remain constant. So as you saw here, that I0 should be a function of depth, while it's going I0 is changing. But the very straight approximation in the kinematical theory is that the I0 is a constant. So every volume of that one particular crystal is there, and the size of that crystal which we are doing the diffraction should be very, very small if you want to this be applicable. And the second approximation is once again very huge, that you can see no one can stop this scattering and re-scattering and re-scattering. But what we assume that once it's scattered, this goes out of the volume of that crystal, and there's no scattering taking place. So it's two very huge approximation that I0 is not a function of depth, and there is no secondary scattering. It's a very huge approximation. But what is very surprising that using this approximation, the theory got that gives almost 98% correct scattering intensity, and that's what mostly we use in all this calculation of powder diffraction using Rietveld refinement. And there is some correction is applied. I think the best person will be the Rietveld or P.D. Babu to ask. So this shows that actual crystal, which is, even if it may be very large, and actually size it may be matching with the JAI, actual JAI, but the actual currently scattering volume, which is this one, is very, very small. It is just capital D. So the capital D is much, much smaller than the JAI. So this is very good sample for doing powder diffraction and calculating the intensity using kinematical approximation. So if the dynamical scattering is taking place, then the intensity is scattered. So that is the case where if your crystallite size is larger or at least equal to the JAI, and then the intensity is calculated is just proportional to F. Usually we are more comfortable, familiar to this equation, but this is only applicable when your crystal is ideally imperfect, or the what language is used, ideally imperfect, and then only it will follow. The imperfect means it has a mosaic structure such that each mosaic size is much, much smaller than the corresponding extinction distance. So if it is matching with that, then the intensity will be given like this. If it is much, much smaller than that, then it will be intensity will be a square of the scattering universal structure factor. So in any scattering, there is hierarchy. Just like everywhere, there is a hierarchy. If you have to reach a person, there will be a hierarchy, how to do, or if you want to learn something, there is a hierarchy. So you have to learn first thing first, and then second thing next. So if X-ray scatters, so it's purely electromagnetic interaction with the matter. So what X-ray sees, since it's mutually perpendicular oscillations of electric and magnetic field, so both interactions with matter are electromagnetic. And every matter inside has charged particles like electrons and protons. So the incident X-ray, the electric field of the X-ray interacts with this charged particle. One can always ask what happens to the magnetic field which is oscillating. So that will interact with the whatever magnetic moments are inside, and that is altogether different area of magnetic scattering. What we all deal today and will be dealing is the charge scattering from the electrons and not from its magnetic moment. Magnetic moment scattering, I think P.D. Babu and others have already discussed. If you want to see them, the best way to go through neutron scattering. But of course, there are beam lines, I think around Spring 8, where you can study magnetic scattering from using X-rays also. But of course, you'll have to use very high energy X-ray ranging from around 250 kilo electron volts. That is only available on synchrotrons. So X-ray interacts with this proton and electron, and they scatter. But since proton is very heavy, you can get from this equation. So I just I will follow this function scattering principle. So the charged particle will feel the field of the electric field, oscillating electric field, and they will start oscillating. Once again, there are some assumptions here that whatever charged particle is interacting with this incident X-ray, it must be infinitely tightly bound. That means it should not come out of from its location. Otherwise, it will do simply the Compton scattering, and it will be inelastic scattering. You will not be able to see any diffraction. So, of course, all the atoms are tightly bound within the, electrons are bound within the atom, and proton also. So, they will just oscillate at its position, and just like oscillating a string, you can see that the waves are propagating. So, the X-ray, this will propagate, the electric field will propagate in this direction, and one can just calculate what is the amplitude of electric field at certain point using simple electrodynamics, and the square of that will be the intensity scattered at that point. Since electron is very small, and since the scattered amplitude at certain point will depend on the acceleration of the particle, so the acceleration will be very small if this mass is 1,000 times larger. This is the mass of electron, and since the mass of the proton is sorry, this is wrongly written. Okay, no, this is correct. So this acceleration due to electron, this will be 1,000 times larger than the acceleration of the proton. So the scattered amplitude at certain points will be almost 10 to the power 6 times smaller than the X-rays. So therefore, most of the time we don't talk about the nuclear scattering from a positive particle as the protons in the nucleus, because the intensity will be almost 10 to the power 6 times smaller. It will not even match with the background. So practically we forget that, and we only just discuss about the scattering from electrons. So if electron scatters, so this is the equation, and this is basically the scattering cross section of the electron, the e to the power 4 minus n square c square to the power 4, and this r is the distance of the detector which is kept, and this is reasonably large. Normally it is around 20 centimeter in our powder diffraction unit, and this gives the polarization factor. This is a characteristic of a transverse wave. In the case of neutron, you will not find such a polarization factor because their wave is very similar to the longitudinal. Basically, it's a de Broglie wave. They are not transverse waves. So, since due to this transverse nature, we have this correction. Otherwise, this could have been simply flat, but angular dependence of electron it comes due to this only. So, at 90 degree, you will find that it will go to half. And when theta is 5 to 90 degrees, the scattering angle, this angle here. So otherwise you start from 1, then after that it will again become 1. So now these electrons are not randomly distributed in the volume. They are going around a nucleus. So they have a nice spherical charge distribution which is almost continuous after a gap between this electron cloud and the nucleus. So you have a annular distribution of the charge cloud, and we're just considering this is a continuous here. We can discuss what type of scattering just a single atom will do. So you have a nucleus here, where you have already omitted the proton that we will not consider. So we'll just consider the scattering by electrons. So I'm just for the sake of discussion, I will treat this as a matter with a continuous distribution of matter. A particle with a continuous distribution of a scattering matter, which is electron in the case of X-ray scattering, and in the case of neutron, it is a nucleus. It's having a continuous distribution here. So we just follow a simple rule of interference. So this wavefront, what is this magenta arrow, is falling onto this particle. Don't think this is a crystal, just a particle which is having continuous distribution of matter, which practically is not possible, everything is discontinuous. But for the sake of discussion, I'm saying it's a continuous distribution of a scattering volume, scattering matter. And in that, we take this as a small red circles up and down. They are exactly diametrically opposite here. So right now, this ray is getting scattered from here, and I'm just considering its phase in this direction. And similarly, this is getting scattered from here, and this is small red square and getting scattered in this direction. The path difference between the two, if the diameter of this particle is a, it will be nothing but 2a, just like Bragg equation, 2a sine theta. And if you divide it by the wavelength, then you'll get the phase. What we said, if the phase difference is equal to the integral multiple, or the path difference is equal to integral multiple of n lambda, they will intersect constructively. So now just see how this phase is changing if you change this angle theta. So if your particle size, because there are a lot of questions, then why there is a flat angular dependence in the case of neutron, but in the case of X-ray, this is having a form factor. And this we say as a scattering length, and this we say as a form factor. So if it is a neutron, then wavelength which is basically a scattering that you are bound to have around 1 angstrom, because you have to get a scattering from the interplanar spacing, the planes inside, and their interplanar spacing is of the order of angstrom only. So you are bound to have a incident neutrons or X-rays which are having wavelength around angstrom. So from 1 angstrom to 2 angstrom, even I will also do. So, but this particle size can be changed. In the case of X-ray scattering, this particle size is one atom, which is of the order of one angstrom. But in the case of nucleus, the size of this particle is 10 to the power 5 times smaller than this, and therefore A is very, very small. So this is the condition for the neutrons. Now we can imagine this, that this A over lambda, what is left is the 2 sin theta into this ratio. That is very, very small. So even if sin theta is changing from 0 to 180 degrees, there will be a phase change in these two rays will be very, very small, and therefore practically there will be no phase difference, and therefore these two rays will be the phase difference will be 0, and there will be always interfering constructively irrespective of the incident angle, and therefore what you will get a flat variation of the intensity by just one neutron, by just nucleus for the neutron scattering. But in the case of X-ray scattering, this is once again of the size of the wavelength itself. So this A over lambda will be of the order of 1, and then this will depend almost on sin theta only. So you can see to the up to a very large extent, this almost follows like a sin. The phase is 0 exactly at 20 theta is 0, but as you increase the phase change will increase, and they will go out of phase, and therefore the scattered intensity in between these two rays will decrease, and as you increase, so after certain angle they will just not follow the sin theta distribution, and they will, because there are other details also. So this is the reason why so that you divide the scatter in two categories. Point scatterer. Point scatterer means like neutron in the case of like the nucleus in the case of neutron scattering, because if the comparison of the wavelength and the particle that decides what will be happen to this angular dependence of the scattered intensity. If the particle size of the scatter size is much smaller than the wavelength of the incident radiation, then this will be almost flat. And if it is of the same order, A of lambda is equal to 1, this will have angular distribution. And that's what we face in the case of X-ray scattering, and that it limits in certain cases. So this just shows practically measured atomic form factor. Since this is decreasing, this scattered intensity by one atom is decreasing, and this decrease is appearing to its spherical form, we term it as a form factor. And in the case of neutrons, it is not getting scattered. There is a customary and best person will say why this is known as a scattering length. Somebody asked today. So that will be constant, and there is terms it is denoted in terms of scattering length. So in the next in the hierarchy comes the atom. So now electron has done its job, and now it is distributed about a continuous charge cloud above every atom, and the atoms are making a molecular structure about this, and that molecular structure is again fitted in a unit cell, and that unit cell is decorated in 3 dimensions in periodic fashion, and that is our crystal, and this is our sample. So basically, the hierarchy of scattering is being starting from the electrons to molecules to unit cells and to the crystal structure. But most of the time, we just stop here. Anybody asks what is the scattered intensity? We talk about the capital F, doing summation over F into exponential minus 2 pi I. That is just a scattering factor by one unit cell. If you arrange the unit cell in different fashion, then scattering intensity pattern will also change, and that's where the isotropy comes, as we just discussed. So a crystal will have a large number of unit cells stacked periodically. Here I've shown that in this direction there are N1 capital N1 unit cells. In this direction there are capital N2, and in vertical direction there are capital N3. So in a normal even 1 micron size crystal, there will be almost in for 13 unit cells of the 5 angstrom size, and each if unit cell is containing 10 atoms, there will be about 14 atoms in a small crystal of 1 micron. And what kinematical theory? So here comes the kinematical theory. We did first assumption that the incident intensity I0 is not changing. So if the crystal is entering from this side and going that side, each of the atoms, this stands for 4 atoms, are getting the same intensity. And once which is getting scattered, isn't scattered from other atom, and that basically simplifies our calculus. So how to add all the intensities is exactly in the same way. This is a double field experiment explained by Young. So for example, at this point, the amplitude is scattered by both the slits are getting added. So in the same way, what we do, so if the one atom is scattering at this point P, and it has a scattering coefficient of this type, it's very simple algebra, not at all tough. So now if you add all this P to the n atom, so the n is very large, number 14, then you will get the total scattered amplitude at this point P, make it a square, and finally you will get the total scattered intensity in this form. What we found here is E0, it is incident E0 square, there is nothing but the incident intensity or the amplitude square of the incident intensity. R is the distance of the detector where you are trying to detect the scattered intensity. And this is F theta and F theta. This is nothing but the initial scattering factor, where it is containing every information of the crystal structure. And now that unit cell has been periodically arranged, having n1 number in X, n2 number in Y, and n3 number in Z. Here basically X, Y, Z is written as X1, X2, Y3. So most of the time we don't. This is basically our geometrical arrangement of diffraction. Most of the time we don't discuss about this. We just remain up to this, and that there is no problem in that. It helps quite a lot. As far as your crystals are in large number, but no sooner your crystals become of having some anisotropy, this starts creating problem, and the peak shapes, everything starts changing. That I haven't discussed here. I'll just skip all this. This I just calculated that this quantity here, I0, for a unit cell arranged in one dimension, and there are only 10 unit cells. So what you will find that in the besides the high intensity peaks, we get some small oscillations, and nobody sees this oscillation in the actual diffraction, because this is for the number 10 only. If you increase this number, the separation of these oscillations will be very, very large, and your diffractometer will not be able to detect them. But it becomes possible to detect when your crystal is artificial. For example, when you are working on multi-layers, these numbers is once again around 10 only. There will be 10 bilayers stacked periodically. So there we see this in the form of kissing oscillations, and from there you can calculate basically what is the thickness of the film, exactly the same what is the size of the particle. So these oscillations give you, but the thickness of the width of these oscillations are connected with the width of the main peak. And therefore in the case of powder diffraction also we connect this diffraction width with the particle size. So he says that the width at the bottom, basically width at the half width will be equal to nothing but the NA, 1 over NA, but width at the bottom is directly 1 over NA. So every diffraction reciprocal lattice point, in principle these oscillations are in principle present there, but for a practical sample which is having particles as large as 1 micron, they are almost merged with that, and you can practically neglect them. Basically, this will be treated as an envelope. It's a very large particle. This will become a single envelope here. So the size of the reciprocal lattice we treat as 1 over NA. So basically, if N is the number of unit cell in X direction and A is the lattice parameter, then the dimension in that is nothing but the 1 over NA. So now I'll just proceed how to explain the powder diffraction. So in a powder sample, we have roughly around very large number of particles. So I have taken the roughly for 9 particles. So and all of them are randomly oriented in different directions. So any of the crystallographic directions of a particle, say if you say 1, 1, 1 of one particle and 1, 1, 1 of the neighboring particle, they will be roughly deviated by a angle of 10 to the minus 9 radian. So it's almost close to that. So if you just consider all of them, what we can convert this powder. So this periodically stacked points here are basically the reciprocal lattice of a single particle, a single crystallite. But when we just consider a powder, then the best thing will be to consider these concentric spheres, because every particle having random orientation in 4 pi third angle. So they will construct a sphere in the reciprocal space. And now just to approach the evolved construction one again, what it tells that you may make a sphere of 1 over lambda. This red circle is showing that as sphere, and this blue thin line is the incident X-ray. So since it is cutting here, so according to the evolved construction, you have to put the reciprocal center of the reciprocal space, the origin here, this one, to this point. So I have kept it here. And now see which are the points which are touching the evolved sphere. So since this is a continuous almost 10 power minus 9 radian is nothing. So this is a almost quasi-continuous distribution of reciprocal lattice points. So one or other point will always touch this. So this is basically the intersection of a sphere with another sphere will be a circle. So basically you will get a radiation going in form of a cone here. I have just shown this cone here. And your detector will be moving on this green line. That is nothing but a diffractometer circle. Or you can put a circular film here in older style. Even today also we put image plates like that. So on image plate, what will be there? The image plate is flat. So the intersection of a cone with a flat will be a circle. If it's properly aligned, it will be a circle. If it's not properly aligned, that is one of the problem with synchrotron machines, that your image plate has to be properly aligned to be perpendicular. So if it is aligned, you will get circles, and each circle will basically represent diffraction from one set of plane. And you can calculate from here, this is nothing but the 2 theta, you will divide it. So basically, this thing becomes a calibration. So we can get the D spacing from that. I'll just skip all this. This shows a diffractometer. Okay, this is very old. It was purchased in UGC-DAE Indore Center in 1992. It is still working. I think this is one of the best diffractometer in our department, and this is very nice data here. So we have some low temperature attachment for this, which is in liquid hydrogen based, but currently we have updated this with a CCR that I will just showing. So finally, from the output of a diffractometer, X-ray diffractometer will be like this. So the x-axis is nothing but the diffraction angle 2 theta, and there will be certain peaks here. Now your journey of Rietveld refinement or analysis of your sample, because all we need is to analyze our sample. And the very first need of any sample is that this should be single phase. And people do report even multi-phase sample also, but they have to accept that there's so much impurity in my sample. So one of the requirement of Rietveld refinement, as our colleagues have already described very nicely, that you can use Rietveld refinement for doing fraction analysis, volume fraction of 2 different or 3 different phases, because this can refine 8 different phases in your sample. So, but most of the time we try to make single phase, and X-ray diffraction, of course, it is used very frequently, but it is not a proper tool to say that it is a single phase. I mean, I am talking about the lab source. So if you really want to claim that your sample is single phase, you'll have to do other characterization like back scattered secondary electron imaging using SEM. So for normal room temperature, even on synchrotron, if your impurities are less than 5%, you will not be able to see them. But in certain measurements, physical property measurements like magnetization measurement, if that 0.5% is having high magnetic moment, then it will overwhelm, it will interfere your physical property measurement quite a lot. Maybe not in the resistivity measurement, but in magnetization measurement, it will interfere quite a lot. So what it needs that your sample has to be single phase, and that you have to do yourself. And no software can do that. So what usually people do, almost 90% time that they do X-ray diffraction. So basically they investigate all the present DS spacings, and they make a chart. This is a chart of the 2 theta, and they make a chart of the peak intensity. So this set of D and I is basically a fingerprint of your sample, and that is used to most of the time, 80% or 90% time, to identify your material, what material you have made, whether it is really formed or not. And that's what Dr. Rietveld told, that you compare it and try to index it. So that's the one way. And you just compare with available data on in the literature or the ICTD data bank. So you will say, okay, my materialized form. And if you happen to coincide a different peak, which is not matching with the data bank, then you say that no, my material is having intuitive phase. And to know its volume fraction, most of the time you can use ritual refinement. That's what I have been using most of the time to that. So regarding shape anisotropy, I like to say that if your particle size is around 1 micron or more than that, even if the shape anisotropy is present, you will not be able to see this in at least in the lab source. There is nothing to bother. So there is no problem, you will be there. But if your particle size decreases, as Dr. Rapp was explaining, that when they crushed this in the mechanical ball milling, the particle went very small and there are a lot of strain. So now for analyzing them, we'll have to do ritual refinement. So I will just try to explain how this anisotropy in this shape, basically you will change the peak shape of your pattern. So nowadays a lot of people are working on nanoparticles. So most of the time nanoparticles are really of a spherical size, and of course there will be large number of distribution. So there will be the same sample will have particles as small as 2 nanometer, extending up to 20 nanometer, and they do some particle size analysis using optical methods and maybe electron microscopy, and do make a histogram of particle size distribution. So even for fitting those type of things is possible now. But they will change. There will be very complicated change in the pattern. So now I will try to explain if at all your particles is having a same size of your sample is having same size of particles, whether it's nano or larger. So if it is nano, it means you will assume that your particles are spherical and all of them are having same diameter, nothing to bother, only peak will be symmetrically broadened, and what the Serre formula you apply that, and you get the particle size. But if your sample happen to be a 2-dimensional sample, for example, the graphene nowadays, so your graphene, the lateral side may be as large as several microns. I have taken 2 micron in this, and worked in white side. But the thickness, graphene, of course, they have only 2 or 3 unit cells of the graphite. But practical crystals, some crystals may be 20 nanometer. Similarly, there may be a nano rod which is very large in length, but the thickness is only few 20 nanometer here. So they will be changing your peak shape with your pattern. So here I will discuss how this will change the peak shape. So your crystal is of this type. So many of the equations that I have just shown earlier, here this sin theta term now will start playing its role. This term. So what I have, this will do that. So diffraction from this or diffraction from any crystal is having the information of intensity. There is the information of the unit cell structure factor and the information of the crystal shape also. Since your normal diffractometry is not able to resolve that shape effect, it basically assume it to be very, very small or practically to 0 and up to certain say 1 micron, because if you do 1 micron size crystal, practically it will be very difficult to, so 1 micron size crystal will require a resolution of 0.02 degrees, practical resolution, which any lab setup will not have. And for that, we'll have to go to synchrotrons. And there also, suppose, since you want to resolve the shape anisotropy of 2 micron size particles, the resolution has to be very, very high, even 0.001 or maybe better than that. So don't bother about that. In lab source, you will not be able to see all this. But if your crystal is having a 2-dimensional nanocrystals, that will be able to see in your lab. So the diffraction, that equation of sin squared, 6 sin squared terms, basically they contain the shape information here. So it means the diffraction is nothing but the reciprocal of what is there in the kept in the sample holder. So in the reciprocal, you have a small particle. What will be the reciprocal of this? The diffraction peak, the peak position is the reciprocal of the presence of the periodicity into your material. then what is the reciprocal of the shape of that crystal? That's what those science patterns say. So I will say, don't bother much about that. You make the reciprocal of yourself. So do a reciprocal of 1/2 micron in X direction, 1/2 micron in Y direction, and 1/20 nanometer in Z direction. We'll make a reciprocal of this. So this is basically a two-dimensional sheet, just like a two-dimensional sheet. We have our A4 size paper. We will make a reciprocal of that. It will become a very fine spike. So in normal reciprocal lattice construction, I showed you a periodic arrangement of reciprocal lattice points, and that was under the assumption that your lattice is infinitely large. But what is happening here? Of course, in 2 dimensions, the lattice is infinitely large, but in other direction is highly limited, and therefore the reciprocal of this will become a spike. So now all reciprocal lattice points which are present initially when we considered the crystal to be few micron size will now become elongated. And similarly, in this case, the reciprocal of a rod will become a disc type. So the reciprocal lattice arrangement which was point-like here, the periodic arrangement of points, will now become just periodic arrangement of the spikes. And that's what changes everything in the diffraction. So let us arrangement, I told you how to make the concentric reciprocal spheres. Now if you try to make reciprocal spheres using these spikes, there will be a lot of complicated structures coming out. So I've just considered only these two. This is 1, 0, 0 lattice point. This is the origin. So this is minus 1, 0, 0. This is 1, 0, 0. So let's take how this will change the shape. So now consider that in this case your sheet was basically thin in this 1, 0, 0 direction. This is a tetragonal phase I have considered. So in 0, 0, 1 direction this is thin, and other 1, 0, 0 and 0, 1, 0 direction is very large. So the spikes will extend in 0, 0, 1 direction here, and all reciprocal lattice points got extended. And out of that, I'm just for the sake of discussion, I'm choosing only this 1, 0, 0 and minus 1, 0, 0. So if you come here and now apply the same that you revolve in this 4 pi third angle, so what type of the intensity? You will get a angular sphere in which the red circle which is saying, is showing the representing the central intensity present here. So in this angular arrangement of this scattered amplitude from that that plane, 1, 0, 0 plane and 0, 0 plane, that will have more amplitude or more intensity, you can say. But this will have a smaller sphere in which the intensity will be keep decreasing in the direction. But the larger the outer extent of this sphere, this reciprocal sphere will go up to here, in which the intensity will keep decreasing, because in this expansion of the reciprocal lattice point in form of a spike, in this region, it will be a Gaussian distribution of the intensity. So in the center there will be large intensity, will slowly going down. So in this outer side of this sphere, reciprocal sphere, there will be less intensity, and the inner side there will be high intensity. When we apply this, so when we apply this to the evolved construction, then we will follow the same thing. You will keep this at the origin. This is the incident X-ray, and the origin here. So we have put that sphere in the origin, and now this X-ray, the evolved sphere is cutting this thick angular cell. Initially, it was a very sharp sphere, a sphere with a very small wall thickness. Now it is a very large wall thickness in which the intensity has a distribution. So in this the intensity has, this is getting masked. So in this region, the intensity, the peak intensity will come here, and it will very sharply drop in the lower angle side, but it gradually, please borrow with me, I'm not able to change this. So this will slowly decrease, and it will have a asymmetric broadening of your peak. So now, depending upon the fact that in which direction your two-dimensional growth of your nano flake has taken place, this asymmetry and the type of index which will be that particular peak, for example, in this case 1, 0, 0, will have a asymmetric distribution of intensity, and there is a direct indication that there is some shape anisotropy taking place. Now let us consider the other peak. For example, this one, 0, 1, 0, in which direction they say it has extended. So this is this peak 100 peak will have asymmetric distribution, but the other peak, so the corresponding reciprocal sphere will have almost in this thick angular sphere will have almost in a symmetric distribution of amplitude or the intensity above the center. And when we apply this to the world construction, we find that the intensity will be symmetric about this peak. So what we find, the 100 will have a asymmetric distribution that will be rather narrower, whereas 1 will have a broader distribution, which can be refined as just Dr. Rietveld told, that this can be refined using Rietveld. I think they use some spherical harmonic formalism in this Carvajal program, this full proof. So these things can be refined using Rietveld. So regarding the phase, okay, so I will just describe now a few of my results. All these things I think P.T. Babu have already told you that actual for intensity, it has various terms are there. Scattering intensity formula. So all these shapes, everything is included in this phi term here. And this is giving, this term gives you the what type of crystalline structure you have to choose, and this is responsible for the intensity. This S is a scale factor. I will just skip this because you have already heard a lot about this. These are the basically guiding factors whether your refinement is correct or not. Okay, so I have just a comment here at this point that sometimes we keep just looking at this and deciding that okay, if this is decreasing, if S factor and this is chi-square is decreasing, I might be getting a correct refinement. But and you also keep matching your pattern also, that the fitted point is really going to the very nicely to your observed points. But what I have found in certain papers that even doing this much is also not sufficient. What is required that if you are just solving a new structure, you should also keep your eye onto the refined model. The finally what you have refined, is it really worth reporting? That should be kept wise. This is just a comment. I will also skip here. So this is what I have been doing in Rietveld here, using Rietveld. This is a very old sample of one of the user, Professor Hegde. So once he was very interested in doing cerium Rietveld refinement. It's very simple. There is no refinable Wyckoff position. It's the SSA structure. So basically, he put a lot of germanium inside. He was trying to develop this material as a battery material. Unfortunately, this result has been cited many times, this publication. So this is an example of Rietveld refinement by us in strontium calcium titanate. So this is a very interesting material. Application wise, this has in very high frequency electronics. This is used as dielectric material. So there are a lot of reports on this, that this has a variety of, and there are at least 5-6 different papers we found. There one of my students Said, he's already a very senior scientist somewhere. So he was doing his PhD, and he found that in literature there is very scattered report, a variety of space groups, starting from PNMA to I4 by MCM, and many other space group P21 by M. So and that time we purchased a new microscope. So we thought, let us approach this using convergent beam electron diffraction. So we approached and we found that the PNMA result, which that was the report by many people, it was not matching with the gonism of the fringes, which is basically deterministic regarding the screw axis and glide planes. On the other hand, it was matching very close to the P21212. So basically, we model this this strontium calcium titanate using that, and we refined, and it was matching very nicely. So basically, since X-ray electron scattering is an 10^4 times larger than the X-ray, so we believed more on that result, and we were able to publish in JPCM. So that is where we did the Rietveld refinement of that data using very slow scanning, a very large time, so 34,000 counts those days. This is one of his own, his work only. He was doing some relaxer studies where he put hafnium in the place of titanium, and he found the change in the crystal structure. Barium titanate got changed to a cubic structure effectively with X-ray, maybe in exact not showing cubic structure, but 10% he saw that the lattice had changed, the effective lattice had changed. So for this, knowing the correct lattice parameter, we did Rietveld refinement. But what I realized, because the atomic scattering factor at the higher angles decreases quite a lot. So lab sources are not very enough, but people do report even refined Vica positions in lab source also. But they should be careful, I will say. So this is another example of LCMO. There is another student, Pankaj Sagdeo, who is also faculty now. So he just started manganites. So I never want manganites. So basically, his result. What he found that the function of calcium doping was getting a very interesting structural phase change, and there to refine the later on we realized that most of the phase change is due to the change in the stoichiometry of oxygen and not due to the calcium position. So he found that up to 5% calcium is a structure were getting rhombohedral, and above that it was becoming PNMA. So basically he did a very close data point of the close composition and defined all the compositions. He was having a nice variation in data point in the lattice parameter A and C and then B. So this is the low temperature setup we have, which we just mount on the diffractometer, which I have just shown. And this we have just recently procured, and which can go down to 10 Kelvin. And due to this corona and lockdown, this has got slightly slow down, but maybe it will be available in coming 1 month for the users. So you just keep looking our site. So okay, I will just skip this once again his work. So this is a refinement of a plutonium strontium manganite. This sample we made for doing some in-field structural studies. You have a low temperature high magnetic diffractometer which you made. Okay, which you have basically assembled here, and many of things were developed at CSR Indore. So for that we made a sample, and this I have checked whether the sample is correct or not. So this is one occasion. So what we found that as a function of temperature, the sample goes from I4 by MCM structure to PNM. So basically, we are interested in knowing what is the phase fraction of the orthorhombic FMM phase. So that's for that we used Rietveld refinement, which have all been discussed. The sample once again LSMO for another student. Basically, he has studied the change of stoichiometry. So the initial made sample were all stoichiometric, very close. Delta is almost 0.01. But when we annealed in the presence of oxygen, delta became 0.01, and you can see all the phase transitions. This is corresponding to delta and 0.01. It was showing a lot of phase transitions from the cubic to tetragonal. But when he heated the sample, when we take the oxygen out, all the phase transitions got vanished, and that was confirmed through a specific heat measurement also. You can say the sample with the highest stoichiometry, you see only this. None of the phase transitions are there. And I did a lot some other studies. We did a microscopic study, but there is not time. So this is another studies on multifluidics in barium titanate only. Manganese titanate is reported to be having a perovskite type of structure. We thought, in fact, there was a report on strontium calcium titanate. So we thought, why not to try the manganese doping at the barium site and see if this conventional barium titanate becomes magnetic. So the point was that whether manganese is going to barium site or not. So whatever the people have reported that better you do a spectroscopic measurement of whether if it's going to barium site, then manganese will have +2 charge state. It was checked using soft X-ray spectroscopy technique, thanks to Dr. Fase and Dr. Sukla. So we also found that our sample is exactly following the signals for Mn+2. But when it was communicated, referee didn't agree, and he wanted to know if should give some structural information from diffraction. We had given the same pattern here, but it was just a pattern with a simple But then we found that he wanted to just prove that really it is going to the A side and there is nothing at the B side. Then we changed some refinement strategy, and we put some of the manganese at titanium side, and it was basically the occupancy was programmed in the Rietveld only, in full only, and we found that at the A side we put X and the B side we put 0.1 minus X. When to the run, we found that the final this X decreases to very close to 0, and what is so that we have deliberately constrained X from 0. So if the X is 0, it means there is no at A side, X is 0 here, all of the manganese at B side. So we found that the profile fitting of 110 peak is very poor here. When you put roughly around 0.05%, and 5% at A side and 5% B side, even then the fit quality of this 110 plane is not good. When only when we just decrease X to 0, equal to 1, then it means that B side is totally 0.1 minus 0.1 is 0, and most of all the manganese at A side. Then we found a reasonably good fit, and then it was agreed by the referee and it got published. So this just shows a slide for our low temperature high magnetic field XRD. This is a slide during the installation, but now everything has been covered because they shouldn't sit around and they have to be covered or they'll get exposed. So there is a lead hutch all around this. It's quite safe. One can sit here 2 hours and there is no exposure in the object. So another Rietveld refinement example which I faced during the work of another student, Miss Poonam Yadav. So she did some work on these spinels where the nickel chromate NiCrO4, and there she was interested in putting John Taylor active ion Cu2+ and John Taylor inactive ion Mn2+, and try to see whether there is any macrostructural change taking place or not. And of course, there we got some beam time, and we did some neutron scattering also. So I just the result. Since it was done, because our aim was to go to as low as possible, and we use this this setup. The problem with this setup is that the sample is kept somewhere here. You can see this red marker, and the source is somewhere here. This distance is around 1 meter. In usual diffractometer, this distance is used to be just 20 or 18 centimeter. The incident intensity is very, very high. Here, the incident intensity, the distance is 5 times larger. The incident intensity is almost 25 times smaller. It's very, very small intensity. So in one direction, we have we have focused the beam. Cell focus has been achieved using a global mirror here. So of course, the intensity is still 5 times smaller, and therefore time taken is very large. So most of the time we don't scan to full pattern to get a good pattern. So most of this work was done with a very limited peak scanning and a simple fitting of the peaks. We got the lattice parameter, and that's what is plotted here. So this, for the manganese case, we found that there was no macrostructural transition during the cubic to tetragonal transition at around 160 degree, and the magnetization measurement you see this peak is coming from around 75 degree. So there's no macrostructural transition. But in the case of copper doped sample, we did found some signature of macrostructural transition because the lattice parameter. So this tetragonal phase is further getting transformed into the orthorhombic phase, which is basically a ferromagnetic phase, and then it becomes antiferromagnetic. So at both these points, we can. So this is the dotted line represents the antiferromagnetic transition temperature, and this for the ferromagnetic. So at both the points, we can see that there is some change in the lattice parameter style. Since the intensity was not very good, so we are not very much confident. Although we have we analyze the Vica positions also, but they are not very confident about it because the X-ray scattering by the oxygen is not very high. So that is not reported. Although this whole work has been reported, her interest is also to understand the frustration, because these are not tetragonal phases. What is the nickel is basically a chromium sits on a tetrahedral topology. What is expected that they will be frustrated, and many of there are examples. Many of the system people have found frustration. So what we found during the Rietveld refinement of neutron data. This is last slide from my side. So we found that the manganese case, the moment which you could refine is coming around 1.8 to 10 Kelvin, and the same was for the copper also. So at the A side, the moment is 1.78, 1.80, they're almost equal. But in the chromium, but in the case of at the chromium side, at 10 Kelvin, the moment is only 0.79. So the rest of the moment is basically randomly arranged, giving a very broad hump here. You can see this blue one at the 10 Kelvin. So initially at room temperature it was flat, but as we cool it, of course we got a magnetic peak due to this ferrimagnetic order. But at lower temperature we got a hump also, and that is basically due to the fact that the chromium has not ordered properly, and we are getting hurt. But in the other case, in the case of copper, we got at 77 Kelvin at the chromium side, the moment value is only 0.5. Although, and of course, the nickel and copper are getting arranged ferrimagnetically, and the whole arrangement is ferrimagnetic, the collinear ferrimagnetic. But at still lower temperature of 10 Kelvin, the copper almost gains all of its moment. So why the moment is not fully observed here, and why the moment is fully observed here? It indicates that at this temperature, this chromium moment are having a frustration, is getting removed due to further structural distortion in the sample. But even this phase is also tetragonal, and this is orthorhombic. So in the tetragonal phase also, the system is still frustrated. That's what we concluded. And here I will conclude my talk that X-ray diffraction in conjunction with the Rietveld analysis, as many senior colleagues have told, that's a very useful tool to analyze this phase. And I will say now thank you to everyone. What is in the following is my email address. Whatever questions you can ask, you can ask right now. And what you are not able to ask, if you just happen to realize later on, you can mail to me or mail to any one of us, and all of them will be replying you. Thank you.
Thank you, Dr. Lalla. And there are a couple of questions. So there is a question from Surjalata Devi. Why do we generally take n is equal to 1 first order reflection reflex now, not 2 n?
Yeah, you repeat it slightly loudly. So, why
do we generally take n is equal to 1 first order reflection reflex now, not n is equal to 2 or 3?
Okay. Yes, that's what I explained. That's a nice question. That's what I explained. I just go into that slide very quickly. So, अरे डॉक्टर साहब रुकिए, आप रुक जाइए, मैं लेक्चर दे रहा हूँ. So this is that slide, okay? So here you have written that it is 1. 2D sin theta equal to n lambda. So n is the order of the fringe. So what is basically the interference fringe coming from the X-ray scattering. But in all discussion, in all analysis, we take n is equal to 1 because we can always divide any DS spacing with that integer. So the integer will be either 1 or 2 or 3 or 4, not fractional. 4. So if you are divided by 2, so initially suppose this D10 was 4 angstrom. So if you divide by 2, if n happens to be 2, then it will become D spacing will become 2 angstrom. So you can always consider that peak, particular peak, which you are initially considering to be a second order reflection from D100. Now you can consider that it is a first order reflection from D200. That's all. So similarly for D300, you will get a peak which will be equivalent to a third order fringe due to D100. So you can divide it by 3, and that will be equal to D100 by 3. So it will be D300. So that is n equal to 1. So just to make simplify and to consider that every peak is basically first order fringe one.
Another question is
are you able
okay.
to get it?
Okay.
Hello.
There is one more question. How to calculate and visualize reciprocal lattice for amorphous material?
Yes, how to visualize? Okay, well, there is nice question. So amorphous materials, basically what you have is a random arrangement of atoms. So you just consider one atom and try to consider it as scattering. So I go to this slide. Okay, so I will come to this slide here. So every atom will scatter in all directions like this. So in amorphous materials, most of the time you can consider about second nearest neighbor interaction. Just the interaction is not extending. Interaction means the correlation. The correspondence between amorphous material and a crystalline material is that the structural correlation in the case of crystalline material goes up to the infinity. So every atom is stacked periodically there with a very nice arrangement. But in the case of amorphous material, that structural correlation has decreased to even lower than a unit cell arrangement, more lower than the bond length. So there you will just have to consider just 2 atoms, and it will be a case of Young's double slit experiment, and we'll have some arrangement in Young's double slit experiment to get periodic arrangement of bright and dark fringes. So amorphous materials diffraction pattern will be equivalent to that. It's not that simple, which I told, but the basic is that only. So now, since it is isotropic, there is no preferred direction in the case of amorphous material. There is no anisotropic arrangement of the atoms inside. These are all isotropic arrangement. You will get diffracted intensity in almost all directions, and the intensity will be simply controlled by this simple concept which I've given you: the interference of of the intensity or amplitude is scattered by 2 atoms, and they will be oscillating. And from there you can have the information of the first nearest neighbor and second nearest neighbor and third nearest neighbor, and that is basically termed as radial distribution function. Basically, I have not ever worked on amorphous material, so I will not be replying you in a much better way. So since it is isotropic, so there will be a lot of intensity in all directions, and that will, the intensity oscillation can be understood in terms of this 2-beam interference.
Okay, I can just add to Dr. Lala's explanation. What Dr. Lala has said is correct. So what one can see in a diffraction pattern for an amorphous material is basically you get the first diffraction peak and the second diffraction peak, which are quite broad. So if you now do a Fourier transform of this pattern, taking care of all the corrections, etc. So basically you try to look at the radial distribution functions and then do an analysis, and actually one can arrive at the coordination number, the first nearest neighbor and second nearest neighbor coordination in the case of amorphous materials also. So basically the reciprocal space would of the diffraction pattern, so that means you are going back into the real space, would actually give you the nearest neighbor and maybe the next nearest neighbor coordination. Yeah, thank you.
Yeah, thank you, sir. Thank you. So basically, what Dr. Siriguri basically generalized or unified the analysis technique, that whether your diffraction pattern is from amorphous material or whether it's from the crystalline material, this radial distribution function concept is common in both of them. And in fact, people nowadays are in fact using this data of crystalline material to do many things using this RDF analysis. Yes, Rajiv, any more questions?
Okay. There is one question, importance of low temperature XRD compared to room temperature XRD.
Okay, so room temperature XRD and low temperature is only that when you are loading your sample, loading anyway is at room temperature only, because the room is at room temperature 25 degrees Celsius. But at that temperature, there will be a lot of scattering, but I mean, the development factor will be there. But when you cool the sample, diffractometer wise, there is no difference. It is the same diffractometer, and but only difference is in sample holder. The room temperature sample holder is a simple glass slide which has a very rectangular groove. You put your material, and there is a defined place where you put it properly, that it is well set in the theta axis, and you will get well focused peak line. But in the case of, if you want to do low temperature of the same sample, then we'll have to do some slight arrangement change of the sample loading. We put a cryostat on the theta axis. Diffractometer remains the same, and the sample is now put in the cryostat, which is cooled using liquid nitrogen nowadays. There are systems where you can cool even liquid helium also. And recently we have procured where you can cool using closed cycle refrigeration of the helium based. So there you can go to 10 Kelvin. The difference is that room temperature XRD difference is done just for the phase characterization, whether you have made the sample a proper phase or not. And if at all it is made, if there is any impurity. But once you have characterized this properly, your next step is to do for what you have planned to make this sample, whether you want to do magnetization measurement, whether you do dielectric measurement, whether you do resistivity measurement. There are all sorts of other measurements. Some people are interested in knowing if this sample undergoes a phase transition as a function of temperature or not. There are diffractometers where you can study phase transitions as a function of pressure. We also do phase transition as a function of magnetic field. So there are variety of sample environment, but the diffractometers remains the same. Resolution, everything will remain almost the same. There's no problem. So you cool or use the low temperature if you are interested in knowing the phase transitions. For example, you take example of barium titanate. Barium titanate at room temperature is tetragonal and it is ferroelectric. But if you heat it to above room temperature, of course, this is not a proper example. If you heat it to above room temperature, then it becomes cubic because it becomes centrosymmetric and the ferroelectricity property will go. So there may be people interested if there is a structural change or if any of the observed property is related with a structural change or not. And there you need a low temperature technique or a high pressure technique or a high magnetic field technique. Yes, another question.
Yeah, related to this question, does LTHM XRD identify both geometrical and magnetic phase change? I think he wanted to know, can you do both the structural and magnetic transitions?
Okay, so here, okay, this doubt always remains there. We are saying low temperature, high magnetic field. I just told you, so you can cool your sample, get a structural change. Now, what I am doing, I am cooling the sample and at the same time applying the magnetic field. It doesn't mean, because in my talk itself, I told a term magnetic scattering. If you are getting confused with magnetic scattering, because knowing the magnetic structure, it requires the magnetic scattering, because the X-ray may only see the electromagnetic interaction. It will not do any, okay, so it will not, is not capable of solving that. I'm saying because the X-ray, in lab source, the magnetic scattered part, which will come from the spin scattering, not the charge scattering, that will be very, very small, almost 10 to the minus 6. So practically, we don't talk about that. If you are really interested doing a magnetic structure using X-rays, then you have to go to high energy synchrotron beam line. So we have not developed this for doing magnetic structure. If you are interested in magnetic structure, then you have to do neutron scattering. But what you are interested in knowing that is there any change in the structure in the presence of magnetic field? Just like, is there any change in the structure when I am cooling it? Is there any change in the structure I am pressurizing it? Is there any change in the structure I am applying magnetic field? So that's what we study. So now you can ask, why do you expect any change in the magnetic field? Because many of the magnetic materials, for example, I showed you
plutonium strontium magnetite, where you have done some study. So it is having magnetic moments. So these moments might be coupled with your lattice, your crystal lattice, through the spin orbit coupling. This is a very simple explanation. So when you apply magnetic field, the moments of the manganese will try to align along the applied magnetic field, and therefore they will apply some strain on through the spin orbit coupling on the lattice, and the lattice structure is expected to change. So if structure is changed, fine. You can see initially it was tetragonal, and now that's what we observed, that now it has gone to orthorhombic. So sorry, at low temperature orthorhombic phase insulating. When you apply magnetic field, it becomes tetragonal. So this change in the structure, in the chemical structure, not in the magnetic structure. Of course, the magnetic structure also change that you can do study through magnetic measurements in DSM, other things. So we are not trying to solve magnetic structure using the setup. For that, we'll have to use neutron scattering. There's a lot of discussion about that. So this is just for the magnetic field induced structural change study. Yes, Rajiv.
Okay, thank you, Dr. Lalla. And these were the all questions. And I thank participants also.
So, I think the participants are still online, so they can write on my mail if there really any question regarding using facilities and what other facilities are available. That is, of course, they're on site, but regarding this LTHM and low temperature, they can write independent mail to me for if they were really interested. Okay, thank you. Thank you.
Okay, thank you. Now I hand over to Mumbai Center for further announcements.
Yeah, thank you, Dr. Rajan.
Thank you, sir.
Close the session for the day, and tomorrow morning again we can restart the session from 9:30 or 10 a.m. onwards. The lecture will start at 10 a.m. So we can log in by that time and we can finish this.
9:30 we will log in.
Yeah, by 9:30 we will log in.
This
By 10
conference
we
is
will
no
finish
longer being recorded. This conference will now be recorded.
Thank you to everyone, and we'll see you tomorrow. Bye-bye. Good night.
Okay, sir.
Thank you very much,
Bye.
Dr. Lalla. It was an excellent talk.
This conference is no longer being recorded.
Thank you, Mukul.
Yeah, fine.
Bye-bye.
Okay,
Bye.
so we'll do it. Yeah,
Sure,
bye-bye.
bye.
Bye.